the idea is, Beryl asked me to talk to you about the polarization of light. Now the first question that comes to mind is, what is light? Which actually may be the most difficult question of all. There may come a time that you come to MIT, that you go to college, and that you're going to take courses in physics. And in your freshman year, you will go through a course which we call 802. 8 stands for physics, and 2 is the second course in your freshman year. It's offered in the spring. And when you take that course, you may have an idea afterwards what light is about, but not quite. Then in your sophomore year, you take another course, which is 803, and you may have a better idea what light is about, but not quite. Then in your junior year, when you're a physicist, you take 2 more courses on quantum mechanics, 804 and 805. And once you have taken those 2 courses, you have no idea what light is about. And that's the case with all physicists. All you will know then, how to manipulate those difficult equations which predict exactly what light will do. And that's the only objective of a physicist. But if you ask me, do you understand what light is? I will have to say, no, I really don't. But I have the advantage that I've taken all those courses. And so I can make a prediction about what will happen if we do what. And if I showed you any one of those equations which are behind this, all of you would walk out right now, and that's clearly not the idea. So the idea is today that we will concentrate on a somewhat simplified picture, which is not wrong. And that picture is that light is a wave. And that was first introduced in the 17th century by a Dutchman with the name of Christian Huygens. Actually, a Dutch person would pronounce it as Huygens, but you don't have the ui in your language, and you don't have the ch, let alone that you can say Huygens. So we will just call it Huygens for now. And so Huygens introduced the idea that light is waves. And we now know, but we didn't know that of course in the 17th century, that light propagates with an incredible speed of about 200,000 miles per second. So the light from the moon would take about 1 second to reach us, and the light from the sun would reach us in about 8 minutes or so. So I mentioned the idea that light is a wave. What do we know about waves? Well, you take a pebble and you throw the pebble in the water, and you see water waves. The water bobs up and down, and in fact, the wave also propagates, just like light waves propagate. Water waves propagate at a much lower speed than light. But something is moving. There is an oscillation of some kind. Now, in the case of water, I can see exactly what is moving. I know that water is going up and down. How about now light? Well, that is more difficult. That's why you have to take all those courses and then you still don't know. But I can tell you what we call them, although that doesn't give you much information. We say a light wave consists of, now hold on to your chair, don't fall off it. It's an electromagnetic wave. Doesn't tell us much, does it? All we know is it has something to do with electricity, the same kind of stuff that powers all these lights, and it has something to do with magnets. Magnetism. Here, this is a magnetic brooch. Stick it on, it's magnet. And light has something to do with electricity as well as with magnets. For now, we will forget about this idea that we don't fully understand what light is, and we even forget about the idea that I gave it this difficult name, namely electromagnetic waves. But what I would like to do is to give you some feeling today for what a wave is and for the bizarre behavior of light, particularly when you are going to polarize that light. And you will understand exactly what that means by the end of this lecture. let's first look into the idea of a wave. And for that I would like some assistance from someone. Oh, wonderful. Now there's one thing you have to know. If you're going to help me, everyone in the world may see you 6 weeks from now. If that's okay with you, that's fine. If it's not okay with you, go back. It's okay. Is it okay with your parents? Also okay. Wonderful. Now, you hold this end, you walk back. Go there. Actually, yeah, because I don't want you to run into the table. Just go lower, yeah. Okay, just walk back. What is your name? Lee. Wonderful name. Walk back, Lee. Walking back. Don't let go, huh? Keep walking back, yeah. Walk back. Oh, you're doing great. That's fine. That's enough. So this is a spring. And if I wiggle my hand up and down, remember water was moving up and down, and then the water waves would propagate. If I move my hand up and down, also a wave will move in her direction, and it may reflect and come back at me. That's okay. Light can do that too. Light can reflect off a mirror. So look at a wave. It is a wave. See it move? Oh, you shouldn't shake. You're not allowed to do that. Of course you can. You look, it's a wave. Wave travel. It's a traveling wave. Hold it now for a minute. No, not shaking now. Notice that I was shaking my hand up and down. And so the wave would stay in this direction, up and down. But I can also shake my hand left to right. Look what I can do. That now is the basis behind the idea of polarization. If the wave is going only in this direction, we in physics say this wave is linearly polarized in this direction. You may want to forget about that word linearly, but this direction don't forget, because I'm going to repeat that many times during this lecture. And when I shake it like this, then it's polarized in this direction. But I can also shake it at an angle, like so. Now it's polarized in this direction. And so now, thank you very much, Lee, you did terrific. You did incredible. Thank you very much. Does it hurt? Does it hurt? Well, you have to sacrifice for science sometimes. This was the first time in your life. Yeah, so do I. You coming to MIT? It's terrific, but maybe you will change your mind and you may come to MIT. Help me again. Okay, Lee? So we know now about a wave, even though it was in the spring, wasn't light. We get the idea that you can make it oscillate like this, you can make it oscillate like this, you can make it oscillate in any direction that you would like to. And so, if I now think of light coming straight to you, so you would be at the end of the spring and seeing it coming to you, then some of those waves may come to you and you would see the spring go up and down. The light is now coming to you. A little later it may go like this, and some of it may be like this, and some of it may be like this. Each individual one would be polarized. This would be polarized in this direction. This one would be polarized in this direction, traveling towards you. And the next one may be polarized in this direction and traveling towards you. But if I look at all the light together, some of it polarized in this direction, some in this, some in this, and some in this, there is not one direction which is preferred. All directions occur. And that's what we call unpolarized light. So I'm going to write this down in big letters. That is very important that we understand what is unpolarized light before we will understand what polarized light is. So unpolarized light is this. This alone would be 100% polarized. If all the light that came to me was doing like this, 100% polarized. If all the light was doing like this, 100% polarized. If all the light is coming to me and oscillating like this, 100% polarized. There are several ways in physics that we can change unpolarized light into 100% polarized light. And when you look around here in the classroom, all that light from these light bulbs, from the fluorescent tubes, the light from the sun, all of that is unpolarized. And we are going to convert it into 100% polarized. And there are three easy ways that we can do that. The easiest is that you buy yourself what we call a linear polarizer, of which you have two. If you open the envelope, you have two of them. It looks like a little plastic plate. This is that plate, enlarged, and it is cut in such a way, I will take this off because we don't need this now, and this plate is cut in such a way, you can cut it in many cases because you buy these large sheets, it's cut in such a way that if light, unpolarized light, goes through this plate, that it's 100% polarized what comes out in this direction. And I believe that all these plates have been cut that way, but I cannot be 100% certain. I can't vouch to that. It's possible that some of them are like this, but I don't think so. I think all of them will be like this. So that means if light comes from the back and reaches you, and after it has gone through this plate, all the light is going to come to like this. That's one way we can make linearly polarized light, and that's the first thing we're going to look at. Then there is another way that we can make linearly polarized light, which I will also discuss and demonstrate, and that is by reflecting light off glass or off water. And there is a third way, more difficult. That is if we have fine dust particles and we shine the light onto these fine dust particles, the light will be thrown in all directions. It's not a nice reflection like we have on the mirror. We call that scattering. I will show it to you. That's also a way that you can make polarized light. But let's first now turn to these polarizers, which were invented by Edwin Land, who founded the Polaroid company. Although the idea that you can make polarized light out of unpolarized light was already known in the 17th century. But they didn't have these fancy, nice Edwin Land plates. If this plate were what we call an ideal polarizer, ideal polarizer, then it would mean that if you shine unpolarized light on it, that 50% comes through, so the light is reduced in half, but everything that then comes through is linearly polarized. So a certain light intensity goes in, half of that comes out, but it's all linearly polarized. That's what we call an ideal polarizer. In reality, you never get 50%, you get always something less. Think of it as being an ideal polarizer to get a picture of what these plates will do. So what I want you to do now is take one of these plates, close one eye, and hold the plate in front of one eye. And hold it like this. All the light that you will see now is linearly polarized in this direction. Is this an exciting experiment? No, because you can't see it. Your eye cannot see linear polarized radiation. Animals can, some animals can, not all. Bees can. They can see linearly polarized light, they can know in which direction. But at least I want you to look through it and imagine in your head that everything is now polarized 100% in this direction. And then I want you to put the plate like so, now all the light that comes through is now polarized in this direction. And then I want you to put the plate like this, and now all the light that you see is polarized now in that direction. In fact, some people can see the direction of polarization, but that's a different thing. It takes a tremendous amount of training. Most of you cannot. How can it be that this unpolarized light going through this piece of plastic, that everything comes out like this? That is mind-boggling to imagine what's going to happen. And I agree with you, that is not easy. And that's why most physicists will say we really don't understand light all that well. But we can predict what will happen. If I go back to my spring, when the spring was oscillating like this, imagine that as the spring was I was shaking the spring up and down, and the wave went like this. Imagine that I would make a slot like this. Piece of wood here and a piece of wood there. That wave could go straight through the slot. There would be no problem at all. Here would be that slot, and this wave would go straight through because it moves up and down in the slot. But now imagine that I have light, that I oscillate in this direction. The spring oscillating in this direction. So now it oscillates like this. I'm trying to make you see this in a three-dimensional way. It comes here. Now it hits this narrow slit, can't go through, gets stuck. So here you see that with this spring, you can easily see why this light, which is polarized in this direction, goes through. But light which is polarized in that direction cannot go through because the slot is too narrow. And in that sense, you can perhaps now imagine why unpolarized light can be changed into linearly polarized light. I'm just mentioning this so that you have some idea on what may be going on in that plate, even though that idea is not absolutely perfect. Now there is something that I have to teach some of you, although many of you may know this, but I'm going to need this for the rest of my lecture. And that is the idea of an angle. What is an angle? And how do we express angles? If I have here a circle, and I draw here a line, and I draw here a line, then we call this an angle. And how do we measure an angle? In mathematics, we have adopted, that's a definition. There's nothing that you can understand about it. It's just the way we name things. We call an angle that goes all the way around, so that is what we call a full rotation. So this leg goes all the way around. This angle then we call 360 degrees. Is it logic? No, I would prefer 100 degrees, but we call it 360. I can't help it. That's the way it's called. It's called 360 degrees. Now you think of it, there are 60 minutes in an hour. Equally absurd. Why not 100? Why not 10? Equally absurd is that there are 60 seconds in a minute. Makes no sense. Equally absurd, there are 12 inches in a foot. Why not 10? I don't know. All these things are historical, and we have to live with that. So once you define this angle in 360 degrees, then you now know that 1/4 of a rotation is going to be 90 degrees. So I'm going to make there a picture of 90 degrees, since we're going to need that very badly during this lecture. So if I rotate this leg over 1/4 of a rotation, then it will be like this. And this now 90 degrees. It's 1/4 of a rotation. And this 90 degrees, we have another word for that in math. We call that right angles. So this we say, this arm is at a right angle relative to my other arm. It's the same thing as saying they are at 90 degrees relative to each other. It's all the same thing. We also say one is perpendicular to the other. That's the same thing. 90 degrees, right angle, perpendicular to, it's all the same thing. And as the lecture goes on, I may use perpendicular, I may use 90 degrees, I may use the word right angle. And when it is a right angle, we even put in there often a little square like that. We don't do that in any other angle, only when it's 90 degrees. So this angle, 180 degrees. And this angle, very close to 45 degrees. If I divide this exactly in two, and so on. So now, you should know what an angle is. If I now come back to your two polarimeters, and you put one in front of your eye, then all the light that comes out, if you hold it like this, is polarized in this direction. But suppose now, you put on top of that the other like this. What do you think you will see? Where the two are at 90 degree angles relative to each other, where the two are perpendicular to each other, what do you think you're going to see? Yeah? Absolutely nothing. Darkness. Good for you. And why is that? Well, if the light first comes out this way, then this second polarizer would only be willing to let the light through if it is oscillating in this direction, because that is the direction in which it's willing to let the light through. But there is no light that oscillates like this. And so all the light that comes out here gets stuck in this one and nothing comes through. And so now you see why we gave you two polarizers. So you can now take those two plates and you can hold them in front of one eye and rotate one relative to the other, changing that angle slowly. You can first make the angle 0 degrees. That means you put them both in the same direction. Light will go through. And now when you make the angle larger and larger, you will see less and less light. And when they are at 90 degree angles relative to each other, you will see complete darkness. So try that. Can you see me? Yeah? Good. The light that comes from my face is completely unpolarized. Hold one polarimeter in front of your eye and rotate it. You will see that no matter how you rotate it, you will not see any changes in the light that comes from my skin. Maybe from my glasses, but not from my skin. Do we agree? Now, I'm going to change that. I'm going to hold in front of my face this linear polarizer. So all the light that will come to you from my face is now polarized in this direction. Now with one polarimeter in front of your eye, rotating it, you can make me go away. Now, of course, if you cannot see me, I cannot see you either. So if you hold your polarimeters like this, you should see me. If you hold them like this, you should see nothing. And if you do something in between, you will see some of Walter Lewin, a little bit, but not all. A little dimmer. Yeah? So now you see the idea of what polarimeters can do. The experiment that you just did with your two polarimeters in front of your own eye, I can do here too, of course, with a light coming from this light source. Then I can put a line on here. MIT is not going to like that. There's the line. And I can put one polarizer on there. So you can obviously see through it. The fact that the light is now polarized, we don't see that. But now comes my second polarizer, and I put it right angles. The light is gone. Then you don't see the line anymore. Because this is doing exactly what I was trying to explain. They're now at 90-degree angles. And if I make the angle different from 90 degrees, then you will see the line again. Not very bright, but you will see the line. And if I put them in the same direction, then you'll see the maximum that you will ever see. So I assume that you now have an idea of what happens when unpolarized light goes through your polarizer. Now, one of the things that you will learn if you take physics at MIT or anywhere else for that matter, you will learn how much light will come through the combination of these two, depending upon what the angle is between the two. If they are in the same direction and if they were ideal polarizers, then 50% would go through. If you do it like this, nothing goes through. But you will also be able then to predict what happens at 10 degrees, at 20 degrees, at 30 degrees, and so on. And that was already discovered in the 19th century by Mr. Malus, and that law is named after him. And we call that Malus' law. But I will not go into that in any detail. But we can predict exactly, not only at 90 degrees that nothing will come out, we can exactly predict how much light you will see if you rotate. But keep in mind that even if I rotate them at an angle which is not 90 degrees, this is my first polarimeter, so the light comes through to you from behind here, polarized like this. If I put the second one then in this direction, then it will always be linearly polarized in this direction. That does not change. The only thing that changes is that the light that comes through here is dictated by Malus. Malus will tell me how much light comes through. But it is, of course, non-negotiable. It must be in this direction because my second polarimeter will only let light through that oscillates like this. So that's not going to change. So far, so good as far as your polarizers are concerned that we handed out. Now, I want to go to the second way that we can make 100% polarized light. If we start off with unpolarized light, and we do that through reflection. You can do that by reflecting the light of water, or glass, or plastic, or paint, not metal. If you bounce light off metal, you will not be able to polarize it. And you will see later that that's indeed the case. So here is a plate of glass. And I have some light that falls onto that plate. I make a nice beam of light, sunlight. Light guns for that, and so some light falls onto this plate. A nice beam of light coming in from some lamp here. We always use as a reference line a line which is perpendicular to the surface. Perpendicular, I use that word, 90 degrees angle. This line is my reference line, 90 degrees. And we call this angle if this is glass, not all glass will do it exactly the same way, but garden variety glass that you have at home in your windows, and if this angle is 55 degrees, then the light that is reflected in this direction is 100% polarized. Not at all obvious why that is, but it is 100% polarized. This angle here is the same as that angle there. That's always the case. When light strikes glass, it bounces off just like a billiard ball bounces off the edge of the table. We would say then the angle of incidence is the same as the angle of reflection. This angle is the angle of reflection. And some of that light goes into the glass. In fact, most goes into the glass. That is not polarized. It's really only the light in reflection that is 100% polarized. If you were to look into this light beam, here is your eye, and you see the light coming to you. So here's the light beam coming to me. Then I would see all this unpolarized light coming to me. Remember? Something like this, something like that, something like that. And the ensemble is unpolarized. If I look here into this light beam, after it is reflected, so it comes up to me, it's now 100% polarized in this direction. And I will demonstrate that. And the angle of 55 degrees depends a little bit on what kind of glass you use. It could be different. It could be a little larger, it could be a little smaller. If this is a water surface, the angle would be 52 degrees, which is not so different from 55 degrees. I have here a glass pane of glass. Those of you who can see it, here it is. And I can rotate that. I can rotate it like that. And here I have a light gun. So light, I'm going to strike onto this piece of glass. Most of it will go through, you see it there. I don't want to know about that. That's not going to be polarized. Some of it will go in this direction. That is the light that is reflected. You're going to see it on this center screen. And I can change that angle. I can make the angle close to 55 degrees, in which case the reflected light will be practically 100% polarized, but I can make the angle smaller than 55 degrees or a lot smaller. And when I do that, then we have a situation that the light is partially polarized. Partially polarized. What that means is that a lot of it comes out like this. A lot. But there may be also some like this, and some like that, and some like that. But if the dominant amount is in one direction, we call that partially polarized. If everything is in one direction, we call it 100%. And at that 55-degree angle, it is very closely to 100% polarized. If the angle is not exactly 55 degrees, it's partially polarized. So we're going to have this light beam. Let me first turn on the light so that I know what I'm doing. Shortly, make it completely dark. Oh, by the way, you think, of course, that with your linear polarizer, you will be able to see that the light that hits here is 100% polarized. And the answer is you can't. And the reason for that is that as it comes off this glass, it is polarized. But when it bounces from this screen back to you, it loses the polarization. So you cannot see it. But that's why I have here a linear polarizer, which I'm going to hold into the beam. So we're going to turn all the lights off, make it dark. And let's see whether we can... There is the light beam. So this is the reflected light. And there you see the light that goes straight through the wall. Most of the light actually goes straight through the wall. Only a small fraction is reflected. This is the light that is reflected. I can see it now. Look into the reflected beam. So the angle is now not optimum. I put the angle there somewhere at random. And I will show you that if I hold this large sheet of polarizer into that beam, and if I rotate it around, you will see that the light intensity of the top part is changing. Here it is. Keep an eye on it. Now it's darker, but it's not completely dark, but it is darker than in this, right? That's clear. It's darker. So it's partially polarized, because it's not completely dark, the upper part. This is as good as I can do. But now I'm going to make the angle closer to 55 degrees, which is about here. And we're going to do it again. This is the top part. Now I'm going to rotate my polarimeter. Now, look at that, look at that. It's almost completely dark now. I may not be exactly at 65 degrees. That's not so interesting to me because it may take a long time to get it there. But you see now that indeed this light is very close to 100% polarized. Whereas if I hold the polarimeter like this, the light goes through. And it's simply by one reflection of the glass. So you know a lot. You know what linearly polarized light is. You know what partially polarized light is. And you know that you can make linearly polarized light by using your polarimeters. And you know that you can also make it by bouncing, reflecting light off a surface, like glass or water. Here I have a piece of glass. You can't see it, but believe me, it's there. And under that piece of glass is a word written in very large letters. And when I turn on this light, and I stand here, and I want to read that word, I can't read it. Because that light source reflects in the glass. And if that were the sun, I couldn't even keep my eyes open. It would completely blind me. Can't read that word. But when that light bounces off here and it comes out here, it may not be 100% polarized, but it may be almost 100% polarized if the angle is close to 55 degrees. So now what I can do, I can hold in front of my eye a linear polarizer, and then I may be able to read that message, that secret message that I cannot read now. No, I can't read it. I have no idea what it is. Now I can see it. Now I can't. Now I can. Why can I see it now? Because the light is polarized like this, and with the polarimeter I kill that light. And I want to show that to you, so that it's not an easy demonstration. We have here a television camera. And the television camera is going to look at this word. But with the lamp on, you will only see a glare of light. And then I'm going to hold in front of the camera my polarimeter and rotate it. And I will kill the light, not all of it, by no means all of it, a large amount of that light, I can kill it, because I know it's polarized like this to a large degree. Glare from the glass will go away. At least will be highly reduced. At the camera, which is here. You see, you can't read the message. You can't read. All you see is this big white spot that you see is the glare, the reflection. Imagine, it could be the sun. You're driving your car. Your parents drive the car. You're out in the snow. You look in the direction of the sun. And you see this incredible glare in front of you. Now, you have this polarizer. And you're going to rotate in front of the polarizer. And it says hi to you. That's all it says, hi. It was a nice message. So what I've done now with this linear polarizer, I kill a lot of the reflected light. So now you can see what the message is. But now you cannot. And the reason why I show this to you is that now you begin to see the idea behind polarized sunglasses. Why do people wear polarized sunglasses? And how would you put those directions of polarization in your glasses? If there is the sun and there is water on the road and the sun reflects this awful light in my direction, then it is partially polarized in this direction. And so, when I have sunglasses, what I do not want to do is put the polarimeter in like that. That would let the light through. That would be the worst thing you can do. You would send your polarized glasses back to the manufacturer. Say, the hell with it, I don't want those. But what you do want, you want your glasses to be like that. Because now, the glare of the road, whether it is the sun bouncing off water, whether it is the sun bouncing off snow or ice, makes no difference, always is to a large degree, or maybe totally polarized in this direction, always parallel to the road. So this is what you want. Do any of you have polarized sunglasses on? You do? No, you're not sure whether they're polarized. That's easy to check, sir. Take a look at them. Nope. Oh, you think yours are polarized? Oh boy. Nope. But mine are. Mine are linearly polarized. And it just so happened this morning they broke. Which is bad because I have to go to California today and have a meet with one arm cable. But if I put these sunglasses on, it says hi. If I take them off, I can't read the message. My sunglasses are like this, and the polarization is like this. I can give some of you my glasses and try it, but the problem is these are prescription glasses. So if I gave you these glasses, you don't even know where you are. It would be like you were walking on the water, so I can't do that. But what I can do is show you here that indeed the direction of polarization is exactly as I pointed out. Here are my sunglasses. You see that line through the sunglasses? And now I claim that this is the preferred direction of polarization. And this is the preferred direction of polarization of these pieces that you have. This way shows the light. That's exactly what's happening. Nothing. You cannot see the line through there. But if I rotate this like this, then you should see the light. I can see the light. So I've demonstrated to you that my sunglasses are indeed designed this direction. And so if you have some at home, you can test that because you now have your linear polarizers and you know in what direction those little plates have been cut. Alright, so that was reflection. Let's see what is I have given numerous times at my exams, when I was lecturing here, this famous course 802 that I mentioned to you, which is called Electricity and Magnetism. It's the name of that course. Remember, light was electromagnetic waves, so clearly when you learn about electricity and magnetism, you learn about light. I have asked numerous times at exams to give them 5 pictures. One picture I do this, and in one picture I do this, and in one picture I do this, and I ask the student in what direction should they be polarized. And you get all kinds of answers. But some of them have it right, maybe for the wrong reason. So it is a standard question on our exams. I now want you to look through your linear polarizer at all the objects that we have here around in the room and on the table. There is no strong sunlight that will blind you out. There is no beautiful 50-degree, 55-degree angle. Everything is at random. But if you look very carefully and you rotate your linear polarizer very slowly, you may see, looking at the glass spheres, that you will be able to change the reflected light. And if you look at metal spheres, you will not. Do it very slowly, and you put glass spheres here, here, some metal there, and some metal here. And it depends on where you sit. I can see it very clearly. Some of that light from the fluorescent tubes bounces off at approximately the right angle, and so then it becomes partially polarized. It will not be 100% polarized because the angle is not exactly perfect. You're sitting at random locations, and these objects are randomly placed. It's not as nice an experiment as I did here with this plate. Who can actually see when you rotate them? You clearly see that the light intensity of the glass objects changes, but it doesn't change when you look at the metal. And if it does change when you look at the metal, then I can tell you why. It is possible. It is possible if the metal is very close to the glass, when the light bounces off the glass, it becomes partially polarized. And then it bounces off the metal, it remains partially polarized. But we try to set them up in such a way that that's not possible. If at home you want to test looking around of the reflection of the paint, maybe of the kitchen table, you may also try this on the mirrors that you have at home. Keep in mind that a mirror has an aluminum backing, which is metal. So if you look into a mirror and you think you're going to get polarized light, you won't succeed. It's only the light that bounces off the surface of the glass, not the light that would bounce off the bottom of the mirror, which is the dominant amount of light, which bounces off the metal. The light of a mirror is not linearly polarized, even if you make the angle just perfect. Now, when you look at a rainbow, you see a rainbow in the sky, and that makes us all feel very good, wonderful things. Rainbow. Here's a rainbow. Nice rainbow. There's a rainbow in the sky. You will be able to see that the light that comes from this part of the rainbow is almost 100% linearly polarized in that direction. You will see that when you come out and when it rains and when there's a beautiful rainbow in the sky and you take your polarizer and you rotate it, you will see that the light is polarized in this direction. And here it is polarized like so. Here like so. It is polarized, we say, tangential to this arc. Why would that light be linearly polarized? Well, that's a good question. And that is something that is not part of this lecture, but I will want to give you at least an idea where it comes from. And then I will demonstrate it. The rainbow is formed when sunlight enters water drops, could be a waterfall, a garden hose, could be rain. It enters that water drop. It comes in like here. When it enters it changes direction. In the back here, some of it reflects. This is water. This is air. It can reflect of that transition, just like water, like light can reflect of air to glass, and then it comes out again. And it is this which I have not explained to you, but it is that trajectory which is responsible for the formation of the rainbow. And it is here where the reflection occurs, that the angle of refraction is almost perfect for the transition from water to air. If this angle were 37 degrees, it would be perfect. It's almost 37. It's actually 40 degrees. It's very close to 37. So it is right here in the back of the raindrop that the polarization occurs. Now some of you, before I demonstrate the polarization of the rainbow, some of you will say, well, why do we see colors? Well, that's more than I wanted you to tell today, but it is not an unreasonable question. Why do you see colors? If you look at the sun, or the moon for that matter, then that light doesn't look very much colored at all. In fact, if anything, you may want to call it white light, yellowish white light. But that light contains many colors, surprising as that may be. And if you take a piece of glass, it has this shape, which we call a prism, and if you shine a beam of light in here, and as it comes out, you will see all those colors. You will see red here, you will see blue here, you see some green in between, all other colors. You will see red, orange, yellow, green, blue, violet. Object is able to decompose this white light into these individual colors. This is something that I want you to see first before we get into the rainbow. Here is such a prism. Here is a beam of light, not the sun, but it is very white, that light. Strikes this prism and is right there on the wall. Will make a prism. We call it a spectrum. We'll make a spectrum on the wall. Red, green, yellow, orange. Ready for that? Try that, and I'll make it very dark so you can see that spectrum on the wall. There it is. So the white light, once it goes through this glass, decomposes into many colors. Those colors must have been present in the white light. Can't create them out of nothing. So it decomposes that light because of the shape of the glass. Why is it that we don't see colors when we look at the sun? Why does it look white? Well, that's the way that your brains function. Your brains are strange. And when you bring all those colors on top of each other, your brains tell you it's white light. Whether your brains tell you the right thing or not, I don't know. But you see white light when you bring those colors on top of each other. It is the glass prism that makes them come out in different directions. So that some of the red comes on the left side and the blue goes on the right side. That's why you now can see the individual colors. But if I were to merge those colors, then you will see white light. But that's why you normally don't see them when you look at the sun or when you look at the objects here in this room. Your brains are very strange. So are mine. You can see all these colors here, can you? You see red, green, blue, and violet. Why do you see red here? Because there's only red coming from this part. So your brain see red. Why do you see green here? You see only green because your brain say that's green because there's no other color coming from it. If I rotated that disc very fast, your brains will get so confused because they will see the colors coming from one location, all the colors simultaneously. And you will see white light again. dark, but almost dark. And then I'll spin that very fast, and you will see that your idea of colors is going to fade away. You're not going to see colors anymore. Which proves my point: if you see colors from the same direction, all the colors, your brain fool you. Your brain say, hey, right. See that? This is not part of polarization. This has nothing to do with polarization. But I want you to understand that a water drop is a little bit like a glass prism, except that it doesn't have this shape. It has this shape. But these different shapes can make the colors separate the colors, decompose the colors. That's what's happening with the rainbow. So now, what I will do for you, I will make for you something like a rainbow. Not exactly a rainbow, but it is something like a rainbow. And I will do that with one water drop. Because if I made it rain here in 26100, you would never come back. So we can't do that. So we have one water drop, there it is. In a little glass sphere. And we're going to shine an enormous amount of light right into your face. It's this water drop. And some of it will reflect off the back and will come back. And you will see here an arc, which will be red on the outside, blue on the inside. You will think you see a rainbow. And it is indeed very similar. Now I can't shine this light into your face, so I have to put cover over it, otherwise it will not come back either. Okay. Now, the light on this screen will be extremely faint. What do you expect? I use only one water drop. And let's face it, how much did you pay for this lecture? Right? You can't wish for everything. So it's going to be extremely faint. But it will be polarized. And I will show you that it's polarized along the arc. You cannot use your polarizers, because once the light hits you and it comes back to you, it loses the direction of polarization. Maybe not for 100% of the time. I will give you 30 seconds for your eyes to get used to the darkness. If I don't do that, you won't see anything, because it is very faint. And then I will show you with my polarimeters that when you see the arc here, that I can rotate it around, and I can just in the right direction kill that light with the arc. So the first thing, your eyes have to get used to the darkness. Oh, there's some light there. Turn off. So give this a little bit of time. Nice for the video camera. Now, there is your arc. Can you see it? Now just say yeah if you can see it. Okay. You see that it is red on the outside and bluish on the inside? That's what the rainbows should be. So, I argue now that if you look right at the top there, that the light is polarized in this direction, but almost 100%. Here it is polarized in this direction. Here is my sheet, polarimeter. Notice that I can let all the lights through now in the middle. I'm going to rotate it, and now I kill that light. That is convincing proof that that light is highly polarized, almost 100%. I can do the same here, and let the light through this polarimeter, This is apparently for this sheet the allowed direction polarization. And I rotate it very slowly, it gets darker and darker, and now it's completely dark. Almost nothing goes through anymore. Have you seen this? Yeah. So the light, rainbow, highly polarized. Also the white light inside there. Just below the rainbow you see some white light. You also see that in nature. That light is also, notice, nearly 100% polarized. Because that white light also goes away. Now, from now on, you will always carry on you a linear polarizer. You simply cannot go out on the street without a linear polarizer. I always have in my wallet at least one linear polarizer. And whenever you see a rainbow, you take this linear polarizer and you make sure that that bow is polarized. Maybe the day will come that it is not polarized, in which case you should call me right away. Always carry on you a linear polarizer. Now I come to the third way, the last part, that we can polarize the light. Not by means of reflection, but remember I mentioned fine dust particles. Light strikes fine dust particles. It doesn't reflect in a nice way that it bounces off the glass, but it scatters in all directions. A little bit goes off in this direction, some in this, different direction. We give that a different word, we call that scattering. And when light scatters of fine dust, it can also become 100% polarized, provided you do it just the right way. We have a beam of light coming from below. Later, that's where it will come out. Here, light, beam of light will come straight up. And we will put dust particles in here. And those dust particles have to be extremely fine, which we will use cigarette smoke. As much as I hate to smoke, I will have to do that once. And if these small dust particles are here, and some of this light, which comes up, changes the direction, not as nice as it will do off the glass that it reflects, but some of it will go in this direction, some in this direction, some in this direction, some in this direction. And some will come to you. Some of it will go to you. And if this light came this way, is scattered over an angle of 90 degrees, it's 100% polarized. Why? Forget it. That's not important. I just want to show you that it's polarized. How can we be sure that you will see the scattering over 90 degrees? Well, all of you are almost in perfect condition because the light comes up like this, and so if it goes in this direction, no matter whether it goes there, or there, or there, or there, the change in direction is almost always, no matter where you sit in the lecture hall, 90 degrees. You follow that? It goes from this to this, that's 90 degrees. This to this, 90 degrees. This to this. So all of you are almost in an ideal position to see that light that was scattered off my smoke particles. And it will be polarized, if I draw a circle here, if you're sitting here in the lecture hall, it will be polarized like this. If you sit right in front, it will be polarized like this. If you sit a little bit there, it will be polarized like this for you like this. So I will make an attempt to demonstrate. But there is something that I have to tell you first. You get that for free. It's like the colors with the rainbow. You get them for free, and I don't want you to miss them. And that is that if the smoke particles are very small, that the violet and the blue light are way more likely to scatter than the red and the orange. That's not so easy to understand, but you have to take my word for it. Therefore, if my smoke particles are very small, that smoke will look bluish. Because the light comes up, And it is the blue and the violet that likes to be scattered. The red doesn't like to be scattered, it goes straight through. But the blue likes to be scattered, so you will see that smoke bluish. You may have seen the exhaust of cars sometimes, bluish. People who burn oil coming out of the exhaust, look bluish. Same reason. The sunlight that scatters off the small oil particles, and it looks bluish. So we're going to catch two birds with one stone, namely, I am going to have this beam of light coming from below, and then you will see that the light is blue, and you will also see that the light is polarized, for which you can use your own polarizers, and the polarization will be in this direction, this direction. Before I do that demonstration, I want to show you and the first slide is the slide of stars. Very famous cluster of stars called the Pleiades. And those stars are embedded in a huge cloud of very fine dust. If I can have the first slide, you will see that. There you see these bright stars, and there is dust around. And look at this color of this light, which is scattered. The light comes from the star, scatters off the dust, comes in your direction, and it's blue. Because the probability, the chance that blue light scattered is way larger than red. You see that here in nature, right in front of you. The next slide. See a man on the moon. Now there is no atmosphere on the moon. So if there is no atmosphere, then the sky would look very dark. But this person is walking on the moon and is scuffing his feet, and there are very small dust particles which go up. Here you see that the light from the sun, which comes from the right side, that goes in your direction, looks bluish. Because these are very fine particles. Blue actually is the color that likes to scatter. And I will get back to this because that's the reason why our sky is blue. And if it scatters over 90 degrees, the light will be polarized. That you cannot see in this picture. So now we're going to do this smoke demonstration, which you can use your own polarizers. So the idea being that light comes from below. I'm going to turn that light on. Oh yeah, thank you. Thanks, Marcos. Light. And I have to get the cigarettes going. Make it very dark. Yucky. Okay. So we're going to get some smoke in here from these cigarettes. Now I know that some of you will say that's not blue. Well, that's your problem. I call that blue. And before this demonstration is over, you will also call it blue, believe me. Try to see, if you rotate your polarimeters in front of one eye, that you can change the light intensity of this smoke. And it should be consistent with the idea that it is polarized in this direction. Who can clearly see, if you rotate the polarimeter, that the light intensity of the smoke clearly changes? Just say yeah. Just say no if you don't see it. say no. So I've convinced you, this comes out almost all of it in 90 degrees. It comes up here, and it goes in this direction in 90 degrees. All of you are almost sitting at 90 degrees. Now I will convince you that the color is blue. And the way I will convince you of that is that the color is only blue or bluish if the particles are very small. If the particles are much larger than what I would call very small, then the blue light is no longer preferred. That means the red light, yellow light, green light, and the blue light all are scattered in the same way. So what do your brains tell you? There's white light. Your brains are being fooled. Your brains see all the colors simultaneously, and they say that's white. Is there a way that I can make these particles a little larger and show you the color change from bluish to white? And the answer is yes. All I have to do is something that is awful. Hold the smoke in my lungs for maybe half a minute. And then the water vapor in my lungs will precipitate on the dust particles of the smoke, and therefore they will grow. And if now I puff out the smoke, there will be very small water drops in that smoke, but they are much larger than the smoke particles. And you will clearly see that light that reaches you, that has been scattered now off the smoke that was in my lungs, is distinctly wider than this blue. So if you're ready for that, just remember first this color. Okay, there we go. Color change? So it was blue the first time. I mentioned the sky. The sky is blue. Yeah, the sky is blue for the same reason that the smoke is blue. Namely, in the Earth's atmosphere are many very small dust particles. And even if those small dust particles were not there, in the atmosphere itself, there are small fluctuations of the density of the air. And so if I put you at the bottom of the Earth's atmosphere, which is a big blanket of air, you're here, and the sunlight, say, comes from here, from this direction, so it's very far away, sunlight is like the atmosphere, coming in like so, you look straight into the sun, that's a stupid thing to do, there's where the sun is. Straight. Terrible, don't do that. Look there! What do you see? How can this light ever reach you? Scatters. Scatters of these fine dust particles. So what is the color? Blue. Because blue refers to scattering. Blue and violet are the ones that scatter way more than red and orange. So when you look right there, is it possible maybe that some of that sunlight that scatters of the dust in the sky scatters at 90 degrees? If that's the case, I'm in business. I go with my little polarizers, I look at the sky, and I can convince myself that that part of the sky must be 100% polarized. Of course, there's a whole ribbon in the sky, no matter where the sun is. As long as the sun is above the horizon, there's a whole plane in the sky. So it's 90 degrees away from the sun. The sun is there. This is all 90 degrees away from the sun. If the sun is there, this is all 90 degrees away from the sun. just like this angle here, 90 degrees. And so, if I look at the sky, not only is the sky blue, which I now perhaps understand a little better, but if I look at the direction 90 degrees away from the direction of the sun, no matter where I do that in the sky, with my little polarizer that you have now in your pocket, you can convince yourself the sky is 100% polarized. Why are sunsets red? So beautiful. Well, that you should be able to answer now for yourself. If the sun is very low at the horizon, and you are here is the blanket of air, and the sun is very low at the horizon, the sunlight comes in this way. Of course, the sun is so low in the sky, how much atmosphere this light has to go through. And remember, the blue light is the light that wants to scatter. And then there comes a time that all the blue light has been scattered out, that there is no blue light anymore. Well, then maybe some of the green light will start to scatter. And then maybe some of the yellow light will scatter. And when all these colors have been removed from the white sunlight, what remains is red. And so it is the light that penetrates very deep into the atmosphere that makes it all the way to here, that has no blue anymore in it, no green, not even yellow, and it therefore is red. And there happens to be a cloud here, specially made for us, so the cloud looks red. That red light strikes the cloud. And so therefore, the same reason why the sky is blue is the reason why the sun is red when it sets. Because all this sunlight now must go through an enormous layer of atmosphere. Blue light is gone, green light is gone, and what you end up with is red light. This is what is left over, maybe some of the orange. And that is what I want to demonstrate to you as my last demonstration. So I want to catch with my last demonstration, I want to catch or kill 3 birds with 1 stone. And the 3 birds that I want to kill are, number 1, that the sky is blue. I'm going to make a blue sky for you. Number 2, that if you look at the sky 90 degrees away from the sun, that the sky is 100% polarized. And number 3, if we make this atmosphere huge, that the sun becomes red. All 3 I can demonstrate to you. 1 demonstration. And I'm going to do that as follows. Here is a bucket, small bucket, something in there which is called sodium thiosulfate. I don't know what it is, so you don't have to know what it is. But that's what it's called. Sodium thiosulfate. Here, I'm going to shine in white light. This gun there. And I'm going to put in here, when the demonstration starts, a little bit of sulfuric acid. And you get a chemical reaction. And the chemical reaction in this bucket will make sulfur precipitate, which are teeny weeny little parts of sulfur, which will slowly precipitate. And when these small sulfur particles in this chemical reaction are produced in the atmosphere, this will turn blue. You know why? Because why do you see light? Because the light has to scatter. Blue light is preferred over the red. So you will see that your sky, small as it is, will turn blue. You sit here, you can move it later, but it's tricky to see it. So you will see it blue. For some of you who are at 90-degree angles, which are only those prefers people. So Adrian, you're just sitting at the right location. That light is 100% polarized too, because it comes in like this, goes like this, that is 90 degrees. Not for you. It will be partially polarized for you. For you it will be 100% polarized. Polarization is in this direction. Light comes in, scattered, it's blue for all of you, for you here, 100% polarized in this direction. You can use your own polarimeters to convince yourself of that. But then as time goes on, more and more sulfur will precipitate. And so what do you think will happen with this beam of light that goes through here? What do you think will happen with the color of that beam of light? Almost right, but not quite. Think about what the atmosphere will do. The atmosphere removes the blue. Redder. Exactly. So this becomes red and redder and redder and redder. That's exactly what happens during sunset. When the sun is still this far above the horizon, it looks a little bit reddish, but it's not so fantastic. But it goes farther in, gets redder and redder and redder. And that's exactly what you're going to see with this light beam, which we're going to produce there. I will first throw in the sulfuric acid, because the whole experiment will take a few minutes. When I know for sure that the sulfuric acid is in there, and that I don't get it on my skin, that's very awful. Okay, so the chemical reaction is starting. So you get your polarimeters out, and I have to turn on the light source. It's on. Turn off all the lights. And now the fun begins. Make sure you can see the atmosphere, which is that bucket. And already I can begin to see the color blue. There's no question. That light that goes through there is bluish. And if you're in the wrong position of the lecture hall, just move yourself to a better position. Try to come a little closer to the center. Also convince yourself, for those of you who are sitting right in front of me, near 90 degrees, that is almost 100% polarized. I can use my polarimeter to show that to those who are not in an ideal position by rotating this. Now the line goes through. Now that reflecting beam is almost filled. Where you sit. See the difference? Use your own polarimeter. You should be able to see that. So your sky is blue. If you're at the right angle, you see that it is nearly 100% polarized. I am here, ideal position. Incredible for me. I cannot see the reflected beam anymore now. Now I can. Now I can. Hey, look at the beam at the end. It's beginning to turn a little reddish. You see that? That the beam itself already is exhausted of all its... I look at the sun. My goodness, that is going to be some sunset. You've never seen a sunset like this. Most of you should already begin to feel a little romantic when you see such a sunset. What a great sunset this is going to be. A blue sky. Sky is 90 degrees, scattering, 100% polarized. You can impress your friends with this, believe me. You're out on the beach and you see a sunset like this. Take your polarizer out. You can show that the sky in certain directions is 100% polarized, and you can even tell why the sun turns red. We're going to be close to sunset, I think. Boy, is that red. Oh, that's red, all right. Ah, it must be very close to sunset now. Yeah, I knew it. There goes the sun. All right, I hope you enjoyed this lecture. Thank you. Okay, Beryl. I don't know what your plans are, but I can answer some questions if necessary. Where's Beryl? You have questions? Yeah? Speak a little louder, yeah?
How come towards the end of the reaction, it started to get greener?
Greener? Right here, you mean? Well, to me it looked a little bit redder. Maybe others saw it greener. The redder part I can fully understand, because as the light enters the bucket here, so much of the blue is thrown out that already this beam turned, for me, a little bit reddish. I mean, here it's completely red. So it's completely red here. I wouldn't be surprised that it is a little reddish here too. If you saw it greenish, well, then you may have seen the idea that this was all gone, and this was all gone. So the beam that was left over is a combination of red, orange, yellow, and green. It may have made a little bit of a greenish impression. To me, it would look more reddish. But it should change the color as it does. As the beam gets deeper into the atmosphere, it turns. That's the reason why the clouds turn red. So when you were on this side of the atmosphere, it turned reddish. Oh, there's Lee. I'll come to you in a minute, yeah?
If you were to stick light through a prism and then another prism, would it change back?
Man, you are fantastic. You should come to MIT. That is the experiment that Newton did for the first time, and that made him famous. Indeed, if you take a separate prism and you put it next to your other prism, the colors become white again. You are fantastic. So that means if you do this experiment and you put a second prism like this, these colors become white again. A+.
Well, I see sometimes the sunsets are sort of red, orange, and yellow, and I was wondering why that one was red, orange, and yellow, because I've seen sunsets that are red, orange, and yellow, and sort of little purple and stuff.
You saw it purple? Yeah, well, you see, if you mix various colors, your brains can do strange things. And if you pick random colors here, your brains can see very different colors than the individual colors. And if somehow your brains tell you that you saw purple, I believe you. I never saw purple, but it can happen, yes. Maybe your brains are very special.
Special?
I think you have very special brains.
Well, I am creative in this long buttons, but it's probably that I get mixed up.
Probably. Take your seats. Take your seats, please. My lecture will be about 40 minutes. And after that, I will give anyone the opportunity to ask me questions for about 15 or 20 minutes. So the whole thing will be 1 hour. And it is after that hour that we will do book signing. You can buy the books there if you want to, and I'll sign them here. We'll get back to that later. If you have a pendulum, this is a pendulum, mass m, length L, then you can derive, which I do in class, but I won't bore you with that, you can derive how long it takes for the pendulum to make one complete oscillation. And we call that the period of the pendulum. And I derive in class that that period equals 2 pi times the square root of L over G. You already know what L is. If you don't know what pi is, you might as well leave right now. And G is what we call the gravitational acceleration, which is approximately the same everywhere on Earth, but it is very close in Boston to 9.80 meters per second per second. And you will say, well, that's weird, meters per second per second. What that means is that if you have an object and you drop it from a very large altitude, very high, a few hundred meters high, and I drop it to zero speed, after 1 second it will have a speed of 9.8 meters per second. But after another second, it will add to that 9.8 meters per second, so it's twice that. And after 3 seconds, it's 3 seconds. So now you understand why it is meters per second. And so that's the meaning of G. There's something weird about this equation. Something that must go against your intuition. And you shouldn't feel bad because it also goes against my intuition. So we have the pendulum, and suppose I bring the pendulum all the way out here. We call that the amplitude of the pendulum, and we let it swing back and forth. There's a certain period. But now we bring it out only this far. It doesn't have to travel very much at all. Doesn't that make a difference in the period? The equation says no, it doesn't. Because if it did make a difference, there would be in that equation the amplitude, which is not. And I'm going to demonstrate that to you, that it is quite remarkable that indeed that period is independent of amplitude if you don't go to extreme values of the amplitude. There's something else in here which is even more non-intuitive. And that is, doesn't it matter whether the bob, we call this the bob, whether it is 1 kilogram or 500 kilograms? You would think, well, that must make a difference in the period. But the equation says, sorry, it doesn't. And I'm going to demonstrate that to you too. We have here, by the way, if you ever want to test this pendulum, this equation for yourself, put in L equals 1 meter. And use this number, you will get a period of 2.0 seconds. Very easy to do at home. You make 1 meter, you put an apple at the bottom, and you swing it. No, the 1 meter has to be accurate. You see that it's going to be 2.0 seconds. Our pendulum that we have here is really the mother of all pendulums. Look at it. 15.5 kilograms. And the length of this pendulum is 5.21 meters. However, you must understand that it is very difficult to measure that to very high accuracy. And so there is an uncertainty in the measurement of the length that we have to be honest about, because we are physicists after all. And the uncertainty we estimate is about 5 centimeters. So we could be off by 5 centimeters. That means that is 1%, 5 centimeters is 1% out of 521. But since L only shows up as the square root, it means the uncertainty in the time that we predict is only 0.5%. And if you don't see the reason why the 1% becomes 0.5%, that's okay, then just forget about it. You take my word for it. So now, I can make a prediction. So I predict, using this equation, that's all I do. I put in 5.21, I put in 9.80, I multiply by 2 pi, and I make the prediction that the period of that pendulum is 4.58 plus or minus 0.02 seconds. Why the plus or minus 0.02? Well, that is the 0.5% uncertainty due to the square root of L. And you can immediately see that 2 is about 0.5% of 458. So my prediction can be no better than that. Now comes the problem. I have to measure the period to convince you that it is independent of amplitude and to convince you that it is independent of mass. So the biggest problem now is Walter Lewin himself, which is my reaction time. How actually am I able to make that measurement? That has nothing to do with our lack of knowledge of the exact length. Now, the last time that I gave this lecture with the pendulum is 12 years ago. I was 63. And at that time, I told the class, my reaction time is a tenth of a second. And it was. But now I'm 75. And so, my reaction time is no longer 0.2 seconds. What is it? Well, I do not know, but I have a feeling that if you want to be kind to me for a change, let us assume that my reaction time at age 75 is now 0.2 of a second. So if you can live with that, then every measurement that I make, no matter how long it is uncertain to 0.2 of a second. Do not confuse that with that 0.02. That has to do with the length. So, I'm going to first make a period measurement at 5 degrees and then at 10 degrees amplitude. And I'm going to measure 10 periods, not 1. Some of you may think, well, isn't that a waste of time to do 10 periods if you can get away with 1? You will very quickly see why it is 10. You will see. So the 10t is then going to be some number, plus or minus, my own inability, which is my 0.2 second reaction. I can't change that. And so then I do it at 10 degrees, and then we get again 10t, we get a number, and then we get again plus or minus 0.2 seconds. And I'm going to demonstrate to you that within the uncertainty of the measurements, that I get the same numbers in all 3 cases, within the uncertainty. So, if you're ready for that, you see here the timer, all of you can see, and here you see the pendulum, and I have 2 marks on the floor here. If I hold the bulb here, then it is 5 degrees, this is 5 degrees, and when I hold the bulb here, it is 10 degrees. Timing is not easy. The best way to do it is to start the timing when the pendulum comes to a stop. That is rather well defined. And then you let it swing 10 times, and then when it comes to a stop, you stop it. And it would help me if you would count how many oscillations we have made. Because then I don't have to look at it. All I have to do is when I come close to 10, I have to watch for the moment of stopping and then I will end it. So, we'll do this first at 5 degrees. I'm going to start it when it comes here. Yeah! Okay, now you come. You're doing very well. You're going to pass this course. .7, so that becomes that t. That means this whole equation now has to be divided by 10. Now you will see why I measure 10 oscillations. So t is going to be 4.57 plus or minus 0.2 divided by 10. That is plus or minus 0.02 seconds. And you see, comfortably within the prediction. Maybe my reaction time is a little better than 2/10 of a second. Don't count on it because you haven't seen the rest yet. So, Now 10 degrees. That moment is crucial. That moment is crucial. That's where you can lose 4/10 of a second and then you look like an idiot in front of your students. That we have to change the mass of this object. And the way that I'm going to do that is prominently demonstrated on the cover of my book. Yes, I'm going to hang on that pendulum. It is a difficult demonstration. First of all, it is painful, it really is. Second, timing is tricky, because when you look at the pendulum and when you see it stand still, you know that's really well defined, plus or minus 0.1 seconds. When you are swinging yourself, however, then you can only do it by sensing the moment that you think you stand still, and that's what I will do. And then you will do the counting. And this is very unpleasant. It is. Oh, there's something else I haven't told you. If you're a good physicist, you will say, if you're going to sit on that bulb, then effectively you bring the mass of the bulb up, and so the length of the pendulum will shorten, and so you get a shorter period. And I know that too. Therefore, I will have to stretch my body so that when it is here, that it is almost completely parallel to the floor. If I don't do that, I will not be able to convince you that the period is independent of the mass. And that makes it very difficult. So I will start it. At some moment you will see when, and then you do the counting. You ready? Okay. Yeah! This happens sometimes. And in fact, nobody knows why. I have to start all over. I did not stop it, I really didn't. Oh, it's still counting? Okay, I have enough energy to give it one more attempt, but not to give it two more attempts. Okay. You ready? Okay. Can't you count a little faster? With Walter Lewin. What is it? 45.9 plus or minus 0.2 period is 4.59 plus or minus 0.02. I told you, physics works. Ball in my hand, and I drop the tennis ball from a certain height, give it no speed, and it will bounce back, then it can never bounce higher than where it started from. If it did, then we physicists would say that is a gross violation of the conservation of energy, and that is the holiest of all laws in physics. It cannot go higher. Suppose the object has a mass m and is the distance h from the floor. Here's the floor, here's the object, h. We associate with the position of that object an energy that has a name. We call that potential energy. And that potential energy is mgh. You already know what g is. Well, h is this distance in meters. So when the object is here on the floor, h is 0. So there is no potential. As the object goes down, it picks up speed. And we associate with speed energy, which we call kinetic energy. And the kinetic energy of an object with mass m is 1/2 mv squared. M is the mass and v is the speed of that object. If the object goes down and it hits the floor, then the potential energy is 0, and all that energy is now converted to kinetic energy. Energy, we believe, is conserved. Now when it hits the floor, some of that kinetic energy may be converted into heat because of the compression. If it were a tennis ball, that would certainly happen. So in other words, when it bounces back, the total energy is no longer the full mgh, but is a little less, and so it won't bounce as high. But there is no way that it could come up higher than h. Suppose it could come after one bounce up here. Well, that would solve the world energy problem. Because you simply sit down and you watch the ball game, and there goes the ball higher, and the second one it goes again higher. If it goes the first time higher, it will do that the second time. And so after an hour, that thing is about a few thousand meters in the sky, and when it comes down on the floor, it has an enormous speed, great amount of kinetic energy, and so you got energy out of nothing. But there is no such thing in physics as a free lunch, so that's not going to happen. So the object can never go any higher than h. And with a tennis ball, there is also what we call the dissipation of heat when it hits the floor. Now, the situation is difficult with a pendulum, because a pendulum doesn't hit the floor, and so there is no heat loss because it doesn't hit the floor. So if you bring a pendulum at a certain distance above the ground, like this, and you let it swing, when it comes back here, it is almost exactly at that same height. Cannot be higher. That would be a violation of the conservation of energy. But since the air drag is so small, there is almost no damping. And in fact, when you saw the demonstration I just did, you may have noticed that you really didn't see this. It really kept going and it kept going. As long as you realize that if I release it from a certain location with zero speed, it can never, when it comes back, be higher than that location. This whole idea is behind demolishing buildings. With a building demolishing, you take a huge mass, you lift it up over a distance h, and then you put your target, which is your house or whatever it is, right at the bottom, when all this potential energy is being converted to kinetic energy, and so this object is hit with an enormous amount of energy in high speed, and you demolish thereby the wall. Here we have a glass plate. You better go out of the way because this is a dangerous experiment. It's a glass plate. So if I bring this object exactly at that glass wall, and if I'm clever enough to let it go with zero speed, it could not break that glass. But if my hands shake a little, and if I give it a little push, then of course it can come back, and it may want to go higher than this, and that would mean I know you guys. Students love it when the glass breaks. That's why they pay such a high tuition at MIT. That's okay, just take that off. Now comes an experiment which is emotionally the most difficult for me of this whole evening. I'm going to put my life on the line to show you that I'm really a believer of the conservation of energy. And you will see how I'm going to do that. I'm going to take the place of the glass, and I'm going to hold this object at my chin, and I cannot move any further back, so there's no cheating. I'm going to release it right from my chin here. You realize, as you have just seen, that the slightest push, and this will be my last lecture. And no book signing afterwards. So I need your collaboration. When I count down from 3 to 0, no noise, no coughing. And I would even appreciate it if for those 3 seconds you would not even breathe. And I have to tell you something. I couldn't sleep all night. I'm going to close my eyes. I don't want to see it. And I'm going to count down from 3 to 0. 3, 0. normally, after this demonstration, tell the class, physics works and I'm still alive. And when an article was written about me in the New York Times a few years ago, on the second page of the New York Times is the wisdom of the day. And the wisdom of the day was, physics works and I'm still alive. White light, like sunlight, is composed of all the colors that you see in the rainbow. If I scatter white light of very small particles, then the blue light is scattered more than the red light, and we give that a name in physics. We call that Rayleigh scattering. Rayleigh scattering only happens when the particles of which the white light scatters is smaller than 1/10 of a micron. That means 1,000 times smaller than the thickness of your hair. So it has to be very, very small. If the particles are as large as half a micron, then there is no longer Rayleigh scattering. There is no preferred scattering for the blue light. All colors scatter equally, and so white light scattered of particles that are half a micron or larger remains white. The dependence of the power of scattering, so I'll give that P, the power, is proportional when we have Rayleigh scattering. This is the only equation that may bother you, to 1 over lambda to the 4th, and lambda is the wavelength of light. And I will not bother you to tell you what the wavelength of light is, that may confuse you, but I will tell you that blue light has a wavelength which is about 1.5 times lower than red light. And so if you take 1.5 to the power 4, 1.5 to the power 4, you get 5. And that means in Rayleigh scattering, blue light has a 5 times higher probability to scatter than red light. And I'm going to demonstrate that to you in 2 complete different ways. The first way that I'm going to do that is to make it completely dark in the lecture hall and have light going straight up here. Then I will light a cigarette, and the smoke of a cigarette has particles that are smaller than 1/10 of a micron. And so the light that you will see that is scattered off the smoke will be blue. So you have seen in front of your own eyes Rayleigh scattering, because the red light more or less goes through. It is really the blue that dominates it, that has the highest probability. So we're first going to do that demonstration to show you Rayleigh scattering of cigarette smoke. And then I have a surprise for you to also show you me scattering. But let's first do the Rayleigh scattering with cigarette smoke. This is also not a pleasant demonstration. For those of you who think that lecturing is easy, no. Make it completely dark, and then I'm going to hold it in there. All lights off, all off, all off. So, we all agree that this is white light which is coming up, and you don't see the light here because there is nothing that scatters it in your direction. So you don't see light here, but now look. Those of you who see blue say, yeah. Those of you who do not see blue, say no. You better see an eye doctor. Now comes the hardest part. If I inhale the smoke and I leave it in my lungs for a minute, there is water vapor in my lungs, and this water vapor will precipitate onto these very small smoke particles. And so the smoke particles will grow. They will become small water drops, larger than 0.5 microns. And that means if I hold it 1 minute in my lungs and puff it out, you will not see blue light, but you will see white light, because you're now in the me-scattering domain. All colors scattered equally. I will tell you that just before I puff it out, and you will see the white smoke, just before I do that, I will remind you of the color that you see now. I will only do that for a few seconds, then I will remove it and I will empty my lungs. Terrible demo. The white light, just say yes. If any one of you has the courage to say no, who did not see white light? Thank you. I'm now going to explain to you, in fact, you could probably guess that, why the sky is blue and why clouds are white. Clouds consist of very small water drops, surely larger than half a micron, which is me-scattering. So the white light of the sun scattered off the cloud, white remains white. So you now, for the first time in your life, may have an explanation why clouds are white. And you should, or may, also understand now why the sky is blue. Here is the ground, and you are here. And here is, say, roughly the top of the atmosphere. And the sunlight comes in like this. The sun is infinitely far away, so the sun comes in like this. The atmosphere is full of very small dust particles, smaller than a tenth of a micron. And even the density fluctuations of the air molecules themselves are clearly smaller than a tenth of a micron. And so you get ideal Rayleigh scattering. So white light comes in, you're standing here, but what is the light that comes to you? Predominantly blue. So the sky is blue. The light that is scattered here comes to you is predominantly blue. So that's why the sky is blue. And so the reason is simply that it is Rayleigh scattering of the dust particles in the atmosphere. If the sun is high in the sky, the total amount of sunlight that is scattered in your direction is only 1%, so it's very little. If the sun is 5 degrees above the horizon, then the sunlight has to travel through a lot more atmosphere. And so I take here a situation which is extreme when we have sunrise or sunset. So the sun is there and the light comes from this side and you are standing here, this is not to scale. This layer of atmosphere is now so enormously large that more than 99% of all the sunlight on the way to you is scattered away. So what is scattered away? The blue is gone. But if you look at 1 overlap that to the 4th, the green is gone. All colors are gone. There's only one color which has the largest wavelength, which by the way is 650 nanometers. I wasn't supposed to tell you, but I decided. So the only light that makes it through you is red. And so that is the reason why the sun looks red, and there is a cloud here in the sky, and that cloud sees light where all the low, small wavelengths have been scattered out, and so this side of the cloud is also red. You can now understand that the more pollution there is in the air, the more beautiful sunsets are. And it is well known that after volcanic eruptions, the sunsets and the sunrises are truly fantastic. It's also the moon that is red when it comes up. And even the stars and the planets, you may never have noticed it because it's not an overwhelming thing. It is the sun that is the overwhelming thing that makes the entire sky red. And so, I have decided that I'm going to create in 26100 a blue sky for you and a red sunset, killing 2 birds with 1 stone. And for the physicist in my audience, I'm going to kill 3 birds with 1 stone. But the 3rd bird comes a little later. I have here a bucket which is filled with sodium thiosulfate. In this bucket. And when I turn the light on, you will not even see any light from that bucket. Nothing is scattered in your direction. I think of that as being the sun, by the way. Now I'm going to add a little bit of sulfuric acid. And when I do that, very small sulfur particles, smaller than 1/10 of a micron, will precipitate in that solution. Radio scattering. And so the light that will come to you is blue. And you will see blue light, just like with the smoke. But now, as time goes on, we will get more and more and more and more of those 0.1 micron particles. And so the light that comes out here has no blue in it anymore. It doesn't have any green in it anymore. It's all scattered in your direction, just like here with the sunset. So what color do you think the sun is going to get? It's going to be red. That's why I said I'm going to kill 2 birds with 1 stone. So I will add the sulfuric acid. The difficulty with this experiment is always, if you put too much sulfuric acid in it, the whole process goes too fast. And if you put too little in it, then you will become impatient. At least MIT students. So I'm going to put this in and stir, and then make it immediately dark. And I want you to look at the sky, which is here is the sky. If you sit all the way there, you don't see it so well. But look, how much did you pay for this? These people have a better view. So just keep looking. For me, it's already beginning to turn a little bluish. We'll just give it a little bit more time. The sun looks just white, light, as it was before. I always have a backup, you see. If this takes too long, then what I do, I add another teeny weeny little bit of sulfuric acid. Speed up the process. I see blue lights, and when I look at the sun, it looks a little reddish already. For the physicist among you, light that scatters over an angle of 90 degrees, this light that scatters in this direction, the people who pay the most tonight, who are sitting right here, the light is also linearly polarized. That was also the case with the smoke experiment, but I didn't mention that. But for those of you who are sitting here, I can show you with my polarimeter, when I rotate my polarimeter, that I can the blue sky completely dark, and I can the blue sky completely bright again. The people who are sitting there, the angle of scattering is not 90 degrees, so they won't see it so well. But you people see it very well, don't you? 100% polarized. Look at that sun. Let's face it, isn't this incredibly romantic? In 26,100, the center of MIT, you are seeing in the lecture hall a red sunset. And in fact, the sun is so red now that I think the sunset is very close. Given in this lecture hall about 800 lectures, and it is wonderful to be back here, but it really hurts to know that this is my last lecture in 2600. I have therefore decided that I want to leave you in style. And the way I will do that is to leave 26,100 in my own private rocket. Thank you. Thank you. Thank you. So now we have about 15 minutes left for questions. And if you have a question, raise your hand. Then Claire will come to you with the microphone. And then I hope we can communicate that way. You phrase the question and I will try to give the answer. So who wants to go first? There's a person there. Yes, we see your hand here. You'll come next.
Thank you for a beautiful lecture. I'm tempted to ask you what pi is.
It's not so easy for me to understand you.
Thank you for a beautiful lecture. I'm tempted to ask you what pi is, but I think I better ask instead.
Well, have you ever had gone to a Thanksgiving dinner?
Okay. Are you familiar with the alleged phenomenon of a green flash at sunset? And
yes.
Can you explain that,
I've
please?
seen it many times. The explanation is not as simple as you may think. I would suggest, and I mean that seriously, since a short answer is not possible, that you look it up on the web. It's well described. I have seen it many times in Austria, in the mountains, that indeed the last fraction of setting of the sun, that you may, but not always, see a green flash. And if you ever want to see it, you have to be with two people. One person has to be standing next to you, and you should not look at the sun. Because if you look at the sun, even though there's almost no sunlight left, your retina is still too overexposed. And so the person next to you, when you look like this, should say, "Look now!" And then you look, and that's the way it is. There's a question right here. Why don't we take that first? And then there's a woman over there. And this gentleman, also. Yeah.
Well, I just want to thank you for the lecture. And I was wondering,
as a youngster, I read a book which told me to stare at the sun, then I can change things by staring at things. Now, what I did was I used to stare at sunset.
You stared at the sun.
At sunset.
At sunset.
For a few.
Not a very good idea. You have to be very careful.
I found out the hard way.
And so you damaged your eyes and you asked for it.
Okay. But the key thing was that after that I was supposed to stay at a white wall, which I did. But I saw a red.
I know exactly what you saw.
Spot moving around here.
Probably the spot was not red but green. It's a well-known phenomenon. So you have indeed done something to your retina, and that is the message that is sent to your brains, then tell you the green after effect. It's a very well-known effect. You don't even have to look to the sun. You can even do it with a light like that and stare in that light for some time, and then all of a sudden look at the white wall and you see a different color. It's a very interesting thing. And physics cannot explain that. But you see, this is neurology. And so it's not our responsibility to explain it.
so this is, I guess, a more personal
Speak
question.
as loud as you can because I have a hearing disability.
This is a more personal question. I was just wondering, what inspired you to become such a great professor?
Why is what?
What inspired you to become a professor and a great one at that?
Can you translate? I can't hear you.
What inspired you?
Why is what?
What inspired you to become a professor?
Oh, that was luck. I had my training in nuclear physics, and then I had some offers for 1 year postdoc to the United States. And for reasons that are not so clear, I picked MIT because a whole new field was born here in Cambridge, Massachusetts, initiated by Professor Bruno Rossi, who was at MIT, executed beautifully by Riccardo Giacconi, who received not too long ago the Nobel Prize for that. That was the discovery of X-ray astronomy. And even though I knew nothing about astronomy at the time, I decided it was time to change fields. So I accepted the offer at MIT. And then, for reasons that are still unclear to me, but George Clark, who is in the audience, knows probably why, they offered me a professorship. And I never left. Does that answer your question? Yeah, you need the microphone here. Oh, we have 10 more minutes, so we can handle quite a few questions.
So I
I sat in on your lectures here, I think about 20 years ago, and I'd forgotten that one thing that I learned from you was how to draw dotted lines on chalkboards. Which I actually used myself when I was a professor for some number of years, so a very useful skill. But here's what I'd like to ask you. I'd like to ask you when you started teaching physics and how your lectures evolved over time.
What was the last question? Didn't get it.
What?
Yeah. I think I was always eccentric. It's true. And so, from day one, my lectures were always different from the mean. But of course, they evolved in a way that grew substantially. And that is not because of the dotting of the line, because I could already do that in high school. Today, there are hundreds of my lectures that can be viewed on the web. 2 complete courses. The first course for freshmen, the second course, electricity and magnetism, and the first course for sophomores, vibrations and waves. They are now being viewed daily on average by 6,000 people all over the world, which is 2 million per year. And so every morning when I wake up and during the day, about 24 questions come to me by email from all over the world. Many ask questions and I answer every single email. But it is amazing that many physics professors want to know how I make those dotted lines. True. There is a 2-minute videotape which someone made. Someone looked at all the dotted lines that I ever drew in 801 and put that in one videotape. It's a riot. You see, Okay, we have time for a few more questions. Yeah, Anna. Anna, please use the microphone, although I'm so close to you that I can probably understand you. Anna is my Facebook friend. I have an art quiz on Facebook twice a week. And then my Facebook friends who can answer the questions are always mentioned every day that they have the answer right. Anna is at or near the top. She almost always has it right. And she sometimes writes me email and she says, Walter, I've worked 8 hours on this one. I really have to give up. I don't have more time. Go ahead.
What is your favorite lecture of all?
I don't have a favorite. I love all the subjects, 801 or 802 or 803. No, I really cannot say I have a favorite. If you ask me my favorite artist, we can talk about that. But we do that on Facebook. There is a question here and there's one there. Ah, we have still 5 minutes for questions. Where are we, Claire? Who has the microphone?
Hello? My name I'm wondering how rainbows relate to ray scattering, do they? And
How rainbows what?
do rainbows have anything to do with ray scattering, and also why are they round?
By my book. It's explained in my book.
Hi, how do you prepare your lectures? How many time do you take to prepare?
It's a very good question. And if I tell you how I prepare them, then my colleagues at MIT are going to hate me. On average, the preparation for one lecture is about 40 to 60 hours. I dry run the lecture in an empty classroom with everything on the blackboard that I'm going to write on the blackboard, pretending that there is a full class in front of me, but there is no one. And I talk to them as if there is one. I do that 2 weeks before the lecture. In general, the lecture is then a little bit too long, so I have to do some surgery. Then 1 week before the lecture, I dry run again. Then I'm very close to the time. And then 5 a.m. of the morning of the lecture, you can ask my wife, I am at MIT, and I give the same lecture, dry run for an empty classroom at 5:30 in the morning, when the lecture is at 10 and the same lecture is at 11. That's the way I prepare. Don't tell my colleagues, they will hate me. By the way, I made an exception for this lecture. I dry run this lecture 6 times. Yeah?
Hi. What advice do you have for a student wanting to become a physicist?
What do you have what?
What advice do you have for students who want to be a physicist?
You have to love it. And if you don't love it, don't touch it. And if you hate it, it is because you had a very bad teacher. I make every student, and not only at MIT, but all over the world, I make them love physics. You can read that in my book, you should buy it. One more question. Okay, one more question. Yeah, this gentleman here.
What do you do for fun besides give lectures?
Art history is my love. Physics is my life. Art history is my love. Thank you. So, the book signing will start. You can buy books. You can buy books in the hall, and you can come down. Now, I have one request. Put in the book a piece of paper and write down with very clear letters to whom I addressed that book. So, if it is for your daughter, and her daughter is Emily, you write for Emily. Even though your name may be Peter, I will write in the book for Emily and sign Walter Lewis. If you don't put in a piece of paper, it's going to take so long. A few days ago, I had a book signing, and I didn't ask them for a piece of paper. So here comes someone from Turkey to me, and I said, what is your name? And he said, my name is Atachia. And then I said, how do you spell that? He said, oh, that's very easy. It's A-T-I-T-T-T-A. And then I said, well, it would be better, wouldn't it, if you write it on a piece of paper. And I couldn't even read it. So please read very carefully, write very carefully the name to whom I should address the book. We need a table. The title of my talk today is The Mystery of Light. It's very mysterious indeed, as you will see. Now, if you want to learn about light, what you really should do, you should come to MIT and take some courses. The first time that you will encounter light is when you take in your freshman year course 802. A stands for physics. It's electricity and magnetism. And when you have taken that course, you have some idea what light is. And then in your sophomore year, you take 803. That's the course, the physics of waves and vibrations. And then you have a much better idea. But then you take quantum mechanics, 804 and 805. And once you have taken quantum mechanics, you have no idea anymore what life is all about. And frankly, if you ask me, do you know what light is? My answer is no. No, not really. However, I can use and manipulate all those complicated equations that I've seen in all those courses. And they allow me to make certain predictions of what light will do under certain circumstances. Does that mean that I have an understanding of it? No, but I know how to turn the crank. It is a recipe, and I know how to use that recipe. Now, I will try to convince you today that light comes in the form of waves. However, that's not the whole story. I could convince you tomorrow, give another lecture tomorrow, that light is not waves, but that light comes in the form of particles. And that is one of the great mysteries of light, and at the end of my talk I'll say a few more words about that. But my goal today is to convince you that light comes in the form of waves. In the 17th century, it was the great physicist and mathematician Isaac Newton, Sir Isaac Newton, who suggested that light comes in the form of particles. But my countryman, the Dutchman Huygens, he said that they came in the form of waves. And that was a key issue in the 17th century. You're probably all familiar with waves. Water waves, for instance, is probably the most familiar. If you tap on the water with a certain frequency, you get beautiful waves that propagate over the surface of the water. You can throw a pebble in a pond and you also see water waves. So waves move with a certain speed, and so we call them therefore traveling waves. And the speed varies a great deal. In the case of water, the speed can be as low as 1 mile per hour, can be as high as several hundred miles per hour. Depends on various things. The tsunami waves can go as fast as 500 miles per hour. Now, sound is also a wave. I produce sound by oscillating my vocal cords, and what they do, they produce in the air high pressure and low pressure areas. They push and pull on the air. When something moves in this direction, compresses the air, comes in this direction, pulls on the air. So you get high pressure and low pressure areas, and they propagate out to you with the speed of sound, which is something like 760 or so miles per hour. Light is also a traveling wave. Light moves very fast. 300,000 kilometers per second, 200,000 miles per second roughly. The sun is 150 million kilometers away from us, so it takes the light from the sun 8 minutes to reach us. To put that in perspective, if a jet plane could fly to the sun with constant speed, then it would take 20 years to reach the sun. We have a name for these light waves. It's a very difficult name. I suggest you first hold on to your chair before I tell you the name. We call them electromagnetic waves. Not only light, but there are other forms of electromagnetic waves, like radio waves, X-rays, infrared, UV, all members of the family of electromagnetic waves. So clearly it has to do with electricity, and it has to do with magnetism. Now, you all are familiar with electricity, and you probably know about magnetism. You have magnets on your refrigerators at home, no doubt. I happen to wear a magnetic brooch today. You see, this is a magnet, and it sticks very nicely. And all of that has to do with light one way or another. Electricity and magnetism is what light is all about. Some of the electromagnetic waves, most of them actually, are invisible. Light is what we can see with our eyes, but infrared you cannot see. Ultraviolet light you cannot see. Some animals can, but we cannot. However, you can feel infrared light. It's the body heat that is infrared. You can feel that. So we have sensors that we can at least detect the electromagnetic waves in the infrared. I have decided to put a minimum of equations on the blackboard, but there is one that is very important, because you're going to see it throughout this lecture, and so if you're ready for this, let us take a look at a wave. Here is a wave, and this could be a water wave, or it could be a wave that you put in a string, in a violin string. And this wave is propagating in this direction. And the speed of that propagation, let's call that v. The separation from mountaintop to mountaintop is called the wavelength, for which we in physics give the symbol lambda. Now, in order to generate this wave, I'm going to tap on the water up and down, and I can do that with a certain frequency. So I'm going to introduce the word frequency for you, for which we will write the symbol F. And that simply means how many times per second I move it up and down. It could be a string, or it could be the tapper on water. So it is the number of oscillations, per second. And we abbreviate that. The unit that we give that is really oscillations per second, but we normally write for that hertz, capital H, small z. And so 10 hertz means that I make 10 oscillations per second. 100 hertz means 100 oscillations per second. Now, there is another quantity, t, which is the period of one oscillation. How long does one oscillation last? It's immediately obvious that if you have a frequency of 10 oscillations per second, that one oscillation only lasts 1/10 of a second. And so therefore t, which is the period of the oscillation, of one oscillation, t is clearly 1 divided by f. So if f is 10 hertz, just as an example, 10 oscillations per second, then t is 1/10 of a second. This should not be too tough for you to handle. Very good. Now, if I move my hand up and down here, if this were a string, in capital T seconds, and if the disturbance moves with a velocity v, then the distance over which that disturbance has moved, that distance is of course v times t. And so therefore there is a key relationship between the wavelength lambda, the velocity of the wave, and the period of the wave. So in this amount of time, the disturbance has moved this far, which is our definition of wavelength. And since capital T is also 1 over f, I can also write that as v divided by f. And this one I want you to hold on to, because that will come back during my lecture again and again and again. In the case of water, the disturbance of the water is perpendicular to the direction of propagation. You see here the mountains, and you see the valleys. They are in this direction, the water goes up and down, yet the wave propagates in this direction. And that we give that a name, we call that transverse waves. Transverse indicates that the direction of motion of the water is perpendicular to the direction of propagation. So they are traveling transverse waves. In the case of sound, the situation is different, because when my vocal cords vibrate, they push the air in, high pressure, and then they suck on the air, low pressure. And so there, the disturbance of the air, the high pressure and the low pressure regions, are in the same direction of motion. That's why it's very difficult to make a drawing of a sound wave. And we give them a different name. We call them therefore longitudinal waves. And longitudinal means that the displacement of the air is in the same direction as the direction in which it moves. Light is also a traveling wave and is also a transverse wave. There are electric and magnetic fields that oscillate, and they are perpendicular to the direction in which the light moves. Now the light can move through empty space. Light can move through vacuum. You can see the moon, you can see the sun, and you can see the stars. And in between, most of it is vacuum. Now in the case of water waves, we need water to make the wave. And in the case of sound, we need air to make the wave. Not only to make the wave, but the wave can only propagate. As long as there is air, I can propagate sound to you. Sound can never propagate through vacuum. We need the air to support the wave. When you look at this wave, for instance, if this were a water wave, the water that goes up and down here never ends up here. So the water itself does not move in the direction of propagation, but simply bobs up and down. And the same is true with sound. The air that I have in my mouth, lucky you, does not end up in your ears, but it is the pressure wave that reaches you. And when that reaches you, your eardrum starts to shake, and then your brains are constructed in such a way that you say, I hear sound. In that sense, you can perhaps compare the sound waves with a queue of people, a whole row of people who are waiting at the supermarket, and at one end, one person goes boom, and then the next person goes boom, and the next person goes boom, and finally, at the end of the row, the last person goes boom. And you see, that person who was standing there did not move along the direction of the wave, but it was a disturbance that moved along the direction of the wave. So clearly sound cannot exist in vacuum. So when you see these gorgeous scientific, these movies, science fiction, and you hear in outer space a huge bang, well, that's a problem, because sound cannot exist in vacuum and cannot travel through vacuum. Light is very different. There's a big difference between electromagnetic waves, light, and in this case, the water and the sound waves. Because in the case of light, since it can go through vacuum, there is actually something that wasn't there before that now is in vacuum. And that is that mysterious electromagnetic field. So vacuum is completely empty space. We do not need any medium there to support the wave, which we did with water and which we did with sound, not with electromagnetic waves. So even though water does never move from this position to this position, in the case of light, there is actually something, electromagnetic fields, that do move and that make it very special. So there is a big difference in that sense, which many people, many of you often do not appreciate. Now comes the question, of course, what is oscillating in the case of electromagnetic waves? Well, what is oscillating somewhere, without you knowing it often, something must be oscillating, and what is oscillating are electric charges. And these electric charges produce spherical waves in all directions, just like sound. When I speak to you, waves move out in all directions. Electromagnetic waves move out also in a spherical way, and they carry with them then this electromagnetic field, which is produced by oscillating charges. Let's try to be a little bit more quantitative and use this equation. We're going to use it for water, we're going to use it for sound, and we are going to use it for light, because those are the three substances today which are at the center of my talk. I have over there a very thin pan of water with a very shallow amount of water. There's only 4 millimeters of water in that pan. And since physics is not only my hobby, but is my life, I can calculate the speed of water waves when there is only 4 millimeters of water. I'm not going to tell you how I do that, but the speed of water waves when you have 4 millimeters of water, that speed is roughly 20 centimeters per second, 0.2 meters per second. You have to take my word for it. If I change the depth of that water, the speed will change. If I tapped on the water with a frequency f, if I did that with 10 hertz, then you can calculate now what the wavelength will be. Lambda then is v divided by f, so that is 0.2 divided by 10, and so that is 0.02 meters, for which we would all say that is 2 centimeters. About this much. And if I tapped with twice the frequency, So the frequency doubles, then the wavelength is twice as small, it's only 1 centimeter. And if I tap at 5 hertz, the wavelength would be 4 centimeters. And this is something that I would like to show you. Maybe nothing new. I want to remind you, without meaning to insult you, that whenever we have a line, we call that in maths 1 dimension. The violin string, if the wave moves along a violin string, that would be a 1-dimensional wave. If we have a surface, such as water, then the waves that travel over water are 2-dimensional waves. They do not just go along a line, but they go out in all directions. And then when we deal with spherical waves, which is sound and electromagnetic radiation, we call that 3D. And I will often refer to this shorthand notation, just saying 1D, 2D, and 3D. So just to warm you up to the idea, let's take a look at some water waves, which then propagate roughly with that speed that I have there, 0.2 meters per second. It may surprise you, but it's a fact that in the case of this shallow water, the 4 millimeters, that if I change the frequency, then the speed of the water wave will not change. So that's important in this case, that we keep the speed constant, and you will see then that there is a change in the wavelength. So we're going to show that to you there. We are tapping on there with a tapper. I want to make it dark. And I have to turn on the TV. And there you go. But this is nothing too exciting, but you are looking here at a 2-dimensional wave, circles that come out from the tapper. We are disturbing the water. The water itself is not moving with the wave, but it's disturbance that moves with the wave. They move very fast, 20 centimeters per second, so there's no way almost that you can follow that, but you can see the dark and the brighter areas, which is of course a lens effect, and one of them represents no doubt the mountains, and the other represents the valleys. And that separation from dark to dark is roughly indeed 2 centimeters. When I look at it here, I can see it better because I don't have any magnification. It's about 2 centimeters. So we are very close to 10 hertz. If I go to a much lower frequency, this is much lower than I did before, then you see indeed that the wavelength increases, still traveling, but it increases. And that was my goal, that I at least shown you a traveling wave, 2-dimensional traveling wave. I don't know. That's not my intention to lower that. All right. So, traveling wave of water. How about sound? So this was water. Sound. The speed of sound in this room is about 340 meters per second. That's non-negotiable. It will change a little bit with temperature. So V is 340 meters per second. Suppose I have an oscillating tuning fork. I have one here. And I oscillate the tuning fork with a frequency of 256 hertz. So you're all experts now. I could ask you, what is the wavelength? I cannot make you see the wavelength, but I can make you hear the sound. And the wavelength then, lambda, is V divided by F. So lambda, longitudinal wave, it's 340 divided by 256, which is about 1.3 meters. And so what that means then, that if you look at the areas, the locations in the air where the pressure is the highest, which can be compared then with the mountains of the water, they are 1.3 meters apart. And the location where the pressure is the lowest, they're also 1.3 meters apart. So you see, it's much easier to draw a water wave than it is to draw a longitudinal wave. So I can make you listen to this. That's just the way it is. But you have no idea, of course, that the wavelength is 1.3 meters. So this is a tuning fork that oscillates 256 times per second. If I increase the frequency, I go to 4,000 hertz, then of course the wavelength goes down substantially. You can check that on your own now. The wavelength becomes only 8.5 centimeters, if I didn't make a mistake in my calculation. And that's a much higher frequency, so your eardrums go faster back and forth, and then the wavelength has enormously decreased. 4,000 compared to 256. So that's sound. So now, sound, by the way, is three-dimensional wave, right? It's a spherical wave that moves out in all directions. It goes in this direction, this direction, this direction, as opposed to the water wave, which is a two-dimensional wave. So let's now turn to electromagnetic radiation. Electromagnetic radiation has a speed through vacuum of 300,000 kilometers per second. It's about the same through air. Little less, but insignificant. The difference is insignificant. And so we will just write down that the speed is 300,000 kilometers per second, which is 3 times 10 to the 8 meters per second. I just assume that you are familiar with the notation 10 to the power 8. It's a 1 with 8 zeros. All right, and if you go from kilometers per second to meters per second, you have another factor of 1,000, and so you get 3 times 10 to the 8 meters per second. Well, let's take FM radio waves, frequency 100 hertz, 100 megahertz, 100 megahertz. This mega, by the way, stands for 10 to the 6. We just write that as a capital M, so let me be cleaner and write it down as 100 times a million, so that it's 10 to the 8 hertz. So the wavelength, lambda, is V divided by F, is 3 meters. So the wavelength of your typical FM radio station is 3 meters. Radar, which would be 10 gigahertz, 10 billion oscillations per second, would give you a wavelength of only 3 centimeters. Peter is quite familiar with radar. How about light? If we have light, I will tell you a secret, and the secret is that I happen to know the wavelengths of light. Remember, I was going to convince you that light is going to be waves. Now, anything that is a wave has a wavelength. And so if I tell you this secret, that light, not all colors have the same wavelengths, but roughly the wavelength of light is about half a micron, and a micron is 1/1,000,000th of a meter. So the wavelength of light is then roughly 5 times 10 to the minus 7 meters. It's half a micron. Many people like to express the wavelength of light in terms of nanometers, which is 10 to the minus 9 meters. Then it would be 500 nanometers. You see both in books. Some people like it to express it in terms of angstroms, and it is 5,000 angstroms. Whatever you prefer, be my guest. But in meters, and since I work with meters here, it is 5 times 10 to the minus 7 meters. So I told you this. So now we can calculate the frequency. Because the frequency now follows from our famous equation. The frequency now equals the velocity divided by lambda. And so the frequency equals the velocity divided by lambda. So that is 3 times 10 to the 8 divided by 5 times 10 to the minus 7. And that is about 6 times 10 to the 14 hertz. times 10 to the 14 oscillations per second. So there are charges, without you knowing it and without my realizing it, which oscillate back and forth, a 6 with 14 zero times per second. And that's a very representative number for light. In the case of blue light, it's a little higher. In the case of red light, it is a little lower. So now, how can I demonstrate this? Now, I demonstrated water for you. We were tapping 10 times per second. And then we went up to an unimaginably high number of 256 times per second, even 4,000 times per second. How on earth can I go up now to 10 to the 14 times per second? Well, I don't have to do anything, just look around you. All the light that you see is generated by charges that are oscillating. So this is the easiest demonstrations for me as I can think of. So there are charges that are oscillating with these frequencies, and they produce the light. Now, whether light consists of particles, as suggested by Newton, or whether they consist of waves, as suggested by my countryman Huygens, which actually should be pronounced Huygens. None of you can say Huygens. And if any one of you can say Huygens, there is a 99.9% chance that you're Dutch. Even Peter, you cannot say Huygens. Try it. Oh, Peter. You're a friend of mine, so I won't say much more then. Huygens, but in the lecture hall in the United States, you call the poor man Huygens. So Huygens suggested that they are waves, and Newton suggested that they are particles. And that was a very controversial issue in the 17th and in the 18th century. And it was not until 1801 that this was settled once and for all. At least that was the belief in 1801. So let's now turn to the proof that light comes in the form of waves. Let's first return to water again. So instead of having one tapper on the water, on the ripple tank there, you can imagine that I have two tappers. So I have one tapper here, and I have one tapper here, and they are a distance d apart. And so here is the line, in the middle of them. So this one is tapping and this one is tapping. They are synchronized, they are connected together, so they always tap with the same frequency. And so this one will start to produce circular waves, just as you have seen. And this one will do the same. So this is then the wavelength. This represents, is my shorthand notation for mountains, and that propagates out over the surface. Now imagine now that I pick a particular point, this point P, and that point P has a certain distance to this tapper, and it has another distance to that tapper. In physics we call this the path length, but it's really the distance. The path length is different for those two. In other words, one wave from one tapper reaches this point earlier than the other wave. This one gets here earlier than that one. Now, if the difference in these path lengths is the difference in path length, if that difference is 1/2 of a wavelength, it's clear that when the mountain arrives from this wave, that the valley arrives from that wave. Because there is going to be a difference in travel time. It would take this wave 1/2 t seconds longer to reach that point than it takes this wave, because half a wavelength takes this amount of time. And so the two waves, as we would say in physics, are 180 degrees out of phase when one wants to drive the water up, the other wants to drive the water down. And the net result is that the water will not move. and this is very characteristic for a wave. The water will stand still. And we have a name for that. We call this destructive interference. The two waves annihilate each other in that point P, and the water will not move. So for instance, if the wavelength was 2 centimeters, as it was during our ripple tank experiment, then it would simply mean that if this pass is 1 centimeter longer than that pass, we would have met that condition. Then the difference in length, in path length, is half a wavelength is 1 centimeter. If I show you in time what this point P will be doing, so I'm plotting here now time, so be very careful. What I was plotting here was not time. I was plotting here actually the water itself. So this was space, now this is time. And I want to know at what time that point P is where. The point P, all the point P is doing is this, up, down, up, down, up, down on the water level. Well, so what you're going to see is something like this. And the separation in time between this and this is then capital T. So at this moment in time, point P was up here, and at this moment in time, it's up again at that point. And so this is then a nice way of saying what the position of P is as a function of time. Now you get destructive interference when the wave from the other one, if the other one were only present, then you would see this. And of course point P has to go with both of them. One wants to do this and the other wants to do this. So point P is going to oscillate with the sum of the two, what we call displacements, maximum displacement we call amplitude, and therefore point P will not move at all. If you add up these two curves, you end up with this. So point P will stay put. Destructive interference. Now, there are many points for which the difference in path is 1/2 wavelength. It is immediately obvious that there should also be a point, for instance, somewhere here on this line. There is somewhere a point here, I just stab at it, say this point, for which this distance minus that distance is 1/2 wavelength. So that point also experiences destructive interference. And so you can construct now on this surface all the points for which the difference in path length to this stepper and this stepper is 1/2 wavelength. Do any one of you know what kind of curve you get? What do we call that curve in math? Don't feel bad if you don't know. I will draw the curve roughly, yeah? It's not a sine wave. You and I talked about it already when you came in. What do you think it is? I have to speak a little louder. Here, I have here a microphone. So my question is, what do you think this curve looks like?
My guess would be a paraboloid, but you said it was hyperboloid.
Yeah, it is a hyperboloid, yeah. But nevertheless, it's a nice try. So you're going to get a hyperbola, and it goes like this. And if you have one here, then clearly you should also have one here for the same reason. Same distance, so you get also a hyperbola here. Because clearly, if this wave from here comes later in time, then the wave from this point comes here later in time. So again, you have a difference between the two of 1/2 wavelength, so 180 degrees out of phase. So there's one hyperbola here and there's one hyperbola here, for which the difference in path is 1/2 lambda, and this one is also 1/2 lambda. But you can construct other hyperbolae for which the difference in path is not 1/2 lambda, but is 1.5 lambda, or 2.5 lambda. And in all cases, will you have destructive interference? And if you don't believe that, you should do your own homework and convince yourself that indeed, this case, the waves are 180 degrees out of phase. The mountain arrives when the other one has a valley. But if the separation is, the difference in path is 1.5 lambda, you have exactly that same situation. Always destructive interference. But now imagine that the difference in path length is 0. And there are lots of points for which the difference in path length is 0. For instance, here, everywhere on this line, the distance to this tapper and to this tapper, exactly the same. So the difference in path length here is 0. This is a terrible abbreviation, distance in path length, dp, is 0. What does that mean? Will you now have destructive interference there, or is there something else special when the difference is 0? Let me get you the microphone, because that's always nice to hear your reactions.
Yes, you'd have something else, and if it's 0, you'd have the same mountain or the same valley.
So what does that mean then? That the two waves
would add.
They would add, exactly. They would add the maximum possible, and that's what we call, we have a name for that, constructive interference. One is destructive, they kill each other. In the other case, they support each other. So now we're going to get constructive interference. So this was destructive. And we have then constructive interference when the difference is either 0 or lambda or 2 lambda or 3 lambda. If you don't believe this, do your homework and you will see that the waves are then again in phase. We say the waves arrive in phase. And if the difference is neither 1/2 nor 1, well, then it is something in between. Then you don't get 0 and you don't get the maximum possible, but you get something in between. If you want to have a rough idea about how many of those hyperbolae you have with destructive interference, we call those, by the way, in the case of water, we call them nodal lines, just a jargon, and we call these anti-nodal lines. So where you have constructive interference, we use the word anti-nodal. Where you have destructive, we use the word nodal. If you want to know roughly how many nodal lines there are and how many anti-nodals there are, anti-nodal lines are, just roughly, it's always 2d divided by lambda. And if you have some time and you spend 10 minutes on the problem, you will see why that is. So always hold on to the idea that you would see the total number is 2d over lambda. d over lambda on one side and d over lambda on the other side. If you add them up, you get 2d divided by lambda. So we get a rough idea. We're going to use that number. That's why I give you that number. I can show you on an overhead then the idea of constructive and destructive interference, is if it isn't clear yet, because I'm going to show you now again that same curve as a function of time, what p is doing, and then I have the option now of moving the two waves relative to each other. So the destructive interference then is for all points on the surface of the water which experience this, that one wave says you have to go down and the other wave says, sorry, I want you to go up. And then the constructive interference is this situation whereby the two waves add up and you get the maximum possible amplitude. You get twice the amplitude that you would get if you only had one tapper. And then there is, of course, everything in between when the condition is neither destructive nor constructive. Let me check my timer. Oh boy, doing very well, Irene, you'll be proud of me. So now I will show this to you. I'm going to try to make an effort to demonstrate this to you. And it is harder than you think. And that's why we have an expert, Marcos, who invaluable in helping me out. Oh, you already set it up. So now we have two tappers. And we're going to tell you that D, the distance between the two tappers, is about 4 centimeters. Sorry that I changed from meters to centimeters, but that makes sense now. If I tapped with 10 hertz, then lambda would be 2 centimeters, right? Remember, 10 hertz would give lambda equals 2 centimeters. So then 2D divided by lambda is about 4. 8 divided by 2 is 4. So you can expect then roughly 4 nodal lines. If the frequency, however, is higher, then you expect, what do you expect? More nodes or fewer nodes? Frequency is higher, wavelength is lower, shorter wavelengths, more nodal lines. So for higher frequencies, you get more nodal lines than you get for low frequencies. And I will try to show you at least 2 or 3 different frequencies. You will see the nodal lines move. That's obvious, of course, because if you meet the condition that here exactly the two cancel each other, that means that the difference in path length is 1/2 lambda. The moment that I change the wavelength, that point is no longer on a nodal line. So the nodal lines will shift, and if you increase the frequency enough, you will see that new nodal lines move in. So you get more of these hyperboloidal surfaces, not surfaces, lines. But in any case, we will only deal with a few of them. And the reason why we deal with a few is because the wavelength is of the same order as the separation between the tappers. So, it is not as easy as you think, and we may have to do some adjustment. And therefore you need a little bit of patience, but we will do the best we can on this. I'll make it completely dark. You ready, Marcos? And I have to turn on the... Okay. Well, this is already not bad. Don't do anything now, Marcos. Let me just go into the lecture hall. So there are 2 tappers now. You have to take my word for that. But when you look at the picture, it is immediately obvious, at least to me, that I see here a lane where the water doesn't move. These are traveling waves, and the water stands still here. It also stands still here. It also stands still there. Can you increase the frequency a little, Marcos? Increase it a little more. Hold it, yeah. So you already see that this lane was moving. It's very clear now. You see no ripples here. You see no ripples here. This is beautiful. And here is, I think, 1. Can we increase the frequency a little more? Let's see whether we can get 4 nodal lines. A little more. Hold it. Yeah. You see 1 here. 1 here. They get closer together. You see 1 here. Oh, I don't see this one coming in yet. You can try a little bit faster maybe, Marcos. A little bit of a... Yeah, there it is. You see it here? Ah, beautiful. 1, 2, 3, 4. So what this means now, that right here on this whole path, right in the middle, that the difference in distance to the tappers is 1/2 wavelength, and here it is 1.5 wavelengths. Here it is also 1/2 wavelengths, and here it is 1.5 wavelengths. The difference here in paths is 0, so those are your antinodal, and here the difference is lambda, and here the difference is 2 lambda, and here the difference is lambda, and there the difference is 2 lambda. So you've seen all the ingredients that are characteristic for wave phenomena, which is interference pattern. That the 2 motions can annihilate each other, can kill each other, the 2 waves, or they can support each other to the maximum possible, which we call constructive interference. Marcos, this was superb. Thank you. I think this is an ideal moment to have a break and to make you think about this. After the intermission, I will then continue this whole way of thinking of interference with sound, and I will bring your intuition to a test. and then we will continue it even to the extreme absurdity, trying to get interference with light, in which case we bring you even beyond what this imagination can handle. Okay, Irene, 5 minutes, do what you want. All right, that was a luxurious break, 6.5 minutes. All right, so now comes a key question. If somehow two water waves can annihilate each other, and given the fact that sound is also a traveling wave, is it possible that somehow sound plus sound gives silence? In other words, is it possible that if I have a loudspeaker here and I have a loudspeaker here, 2000 hertz, nice tone, all of us can hear it, are there then locations in this lecture hall where there is no sound at all? And if that is true, there will be others where there is a lot of sound. Because if there are locations where you have destructive interference, there should be others where you have constructive interference. What do you think? Give it a shot. In the worst case, you're wrong. I'm wrong so often. You shouldn't feel embarrassed about that. So the question is, can sound plus sound make silence? Total silence. Total silence. Who wants to give that a shot? Who is brave enough? Are you afraid? Do you have an opinion? No, you always have an opinion. I will get back to you. You have an opinion? Yeah, I haven't heard much of you. What do you think?
Well, it sounds a wave. That means it can be constructive interference and destructive interference.
So your answer is absolutely yes.
Yes.
There should be locations in this room whereby there is no sound. Who agrees with that? Who does not agree with that? Okay, can you give me your reasons why that doesn't not the case?
I think it's the case empirically, but you have two ears, and depending on the wavelength, will both ears hear that null sound?
Well, all right, but you do say then that yes, there are locations where there is no sound. Whether you can find those locations is then a different issue. Very good. Any other suggestions? Here is someone who has another opinion. Go ahead.
There's a problem of noise. You're not in an isolated environment. There might be no sound contributed from them, but you have the sound from
All right, I hear you, and you of course are right, but what I meant is that the 2000 hertz would go away. And the fact that you're opening your sandwich bag, which is very annoying, that sound I will accept, okay? So that's fine. Well, the proof of the pudding is in the eating. So let us turn on the sound, and I advise you to start walking through the lecture hall and see whether you can find locations where you hear no 2000 hertz. Not just a little, but no. Be my guest. All right, why don't you return to your seats? And I would like you to share with me your findings. So let me first ask you the most difficult question. Were you able to find locations where you absolutely did not hear the 2000 Hz? Did any one of you find such a location? Okay. You noticed that when you walked around that there were certain areas where the sound was substantially stronger than others. Okay. Now let's be a little bit more quantitative to understand what you have done and what you should not have done. More important. The separation of the two loudspeakers is about 2 meters. You could have seen that. And I also told you that the frequency was 2000 Hz. That's key information which you did not use. And I don't blame you for that. In fact, I set you up that way. So the frequency F is 2000 Hz. So lambda equals 340 meters per second divided by 2000. And that translates to 0.17 meters. So that is 17 centimeters. Yeah? We agree? 17 centimeters. How many of those nodal surfaces would there be? You're no longer talking about nodal lines now. It's no longer an hyperbole because the wave is three-dimensional spherical waves. So now the whole thing expands to surfaces. They're going to be paraboloidal surfaces here for which then the intensity should be near zero. And so the number of those nodal surfaces would be 2d divided by lambda, and the distance, as you all could have seen, is about 2 meters. So that is 4 divided by 0.17, and that I think is something like about 24 or so. 24. So there are 24 of those surfaces that come out here, and there the intensity should be close to zero, provided you're not too close to the loudspeakers, because if you're too close to the loudspeakers, then of course the amplitude of this sound is stronger than from that one, and then they can never add up to zero. That's another issue. You have to be a little bit away from it. Without going through the math of exactly where those surfaces are, I can give you an answer which you probably could very roughly have estimated anyhow. And that is, first of all, that the separation in space where those surfaces are depends on where you are. The farther you are away, the farther they are apart, as you saw on the water tank experiment. If you're farther away from the tappers, those nodal lines were farther apart. The same is true here, of course. So they just fan out like this, and very far in the audience there, they are farther apart than here. If you are at a distance of about 5 meters from here, which say Peter is, most of you are, then you can calculate roughly that the separation between total silence and maximum sound, between minima and maxima, between destructive interference and constructive interference, is roughly 20 centimeters. So therefore, you could have stayed in your seats and simply moved your heads and see whether you can find when you move them over a distance of about 20 centimeters. So let's do this experiment again. Who found points of absolute silence? All right. So now I'll tell you what you did and what you should not have done. For one thing, people move their heads way too fast. Your ears are amazingly sensitive. So the locations of real absolute silence are not this wide. They may only be something like a few millimeters, because if you move slightly away from destructive interference, your ear already begins to hear sound. That's number one. But coming back to this gentleman's comment, if the separation between the nodal surfaces and the antinodal surfaces is 20 centimeters, what is about the distance between this ear and that ear? That is about 20 centimeters. Did I do that purposely? The answer is yes. So you will never find a position in the lecture hall whereby you hear no sound. You got to close one ear, and some of you did that. Close one ear completely, move extremely slowly, and when the intensity of the sound goes down, move even slower. And I can assure you that you will be able to find points whereby sound is as close to zero as you can imagine. I was there this morning and I tried it. So I'll give you your last chance. Close one ear and move very slowly. So the separation here is a little shorter than it is there where Peter is. Peter is about 20 centimeters. Wow, you look scary. No one is moving anymore. Who now found locations where, all practical purpose, you can say, yes, it was silent? No one? You didn't. You couldn't find any. Oh, I'm sorry, but I could. Did you find huge differences in sound intensity? You did, but you could never get it way down to zero. Well, one of the reasons could well be we get reflections of sound from the wall. Of course, that's a nuisance. There is also another reason that if you sit right here, then the sound that comes from this one has a higher amplitude than the one comes from this one, because you are closer, and that, of course, you also cannot add up to exactly zero, but you can go close to that. So now comes the last burning question, and that is, if sound plus sound can give silence, I hope I have convinced you that it really can, though you may not have heard it absolutely silent. Is it possible that light plus light can give darkness? So we have water, waves can annihilate each other, sound plus sound can give silence. Can light plus light give darkness? And if that is the case, then light plus light should also be able to give a lot of light. Destructive interference means there would be locations in the classroom where two light sources would give no light, and other locations where constructive interference where you have light. Anyone's guess? Come on, in the worst case you're wrong. So can light plus light give silence? That means darkness. If we can demonstrate that, I think we've made the point that we deal with waves. Yes?
Purely on the assumption that light is a wave that behaves like that, we would be inclined to say yes. But off the top of my head, I don't recall any observational evidence of that, and no fancy science demo, so I would be inclined to say no.
So he is inclined to say no. Do any one of you support the no? Yeah, you support the no, or you...
No, I say yes. I mean, if light is a wave, it can experience destructive and constructive interference again.
So you are a believer. You really begin to believe physics. I've converted him. So who is in support of the idea that light and light should be able to give darkness? Oh boy. And who says no, probably not? You're alone. But John was also alone when he demonstrated that light plus light can give darkness. And I'm going to demonstrate that to you too. So I gave it away. I said that Young in 1801 demonstrated indeed that light plus light gives darkness, can give darkness. And it's very difficult to do the experiment because you cannot do it with two light bulbs. Remember I said the tappers are synchronized. That was easy. It's also easy to synchronize the loudspeakers because they are connected to the same electronics. But how do you synchronize two light bulbs? and that you cannot do. And so the breakthrough that Young made, that he realized that if light is a wave, and if you make the wave go through two openings, so this is one opening, and this is another opening, and this separation is D. So this could be pinholes, but it could also be slits perpendicular to the blackboard, so slits like this. And if you have a light source very far away, and if light is really a wave, then spherical waves would move out. And so by the time they reach here, they come like this. And what you would see is that each one of these openings will then generate waves. You could do a similar experiment with water. We could have shown you the interference pattern with water with one tapper, and then with a wall with two openings. But the two tappers gave us a little bit better result. So Young realized that if you have a light source far away and you have two openings here, that on this side you should have all the conditions then for destructive and for constructive interference. We do this experiment with a laser, which Young did not have. And that's very nice because lasers, of course, are very powerful. The separation that I will use today is 1/4 of a millimeter, and the wavelength of the laser that we will use, the red laser, the wavelength is 633 nanometers, 633 meters, 10 to the minus 9 meters. So if I now ask you how many surfaces are there whereby there is total destructive interference, that would be 2D divided by lambda. It's a high number. And so you can imagine that those surfaces, those destructive hyperboloids and the constructive hyperboloid are close together. We have it set up here, and here we have these two very narrow grooves, 1/4 millimeter apart, and here we have the red laser, and we're going to see there on the screen the results of the light intensity, and that will show you beyond any doubts that you will see locations where it is completely dark and other locations where the light is very strong, and that's where there is the constructive interference. I need my laser because I have to be able to point it out to you. There it is. So you see here areas whereby it's absolutely no light. You see these separations on the screen are no more than maybe 2 centimeters there. So you can imagine how close the destructive interference locations and the constructive interference locations are. But here you see in front of your eyes what Young first did in 1801, which of course equipment that was nowhere nearly as good as what we have here. And this then was in those days convincing evidence that we're dealing with waves. And if you know the distance from here to the wall, which I normally call capital L, and if you know the separation of the two slits, and if you can measure the separation there between darkness and bright and darkness, then you can calculate the wavelength. That's pure math. That is not physics, but that is just pure math. It comes down to hyperbolas and intersect them with a screen. So that is really not all that difficult. So now comes the question, why was this absolutely conclusive evidence that we are dealing now with waves instead of with particles? And this is very fundamental. If light is waves, then you see here on a screen this interference pattern, which goes way beyond the separation D. It goes way beyond, all the way there, all the way to here. Do you see bright, dark, bright, dark? You saw that over a huge area there. Imagine now that light was particles, and that I would throw particles through here, and then some other particle through there, like tomatoes. Then what you would see, so I go one after another, either through one of the opening or through the other, because if it's a particle, it can only go through one opening. You cannot imagine if you throw a tomato that the tomato would split up and that half the tomato goes through one and half through the other. So one particle goes through one opening and then the next one may go to the other. What you would see now is just a pile of particles here and a pile of particles there. You see two light spots, that's it. End of story. That would be typical for particles. But instead, you see this enormous interference pattern, dark, bright, dark, bright. And so it is not so surprising that this was absolutely conclusive evidence that we're dealing here with waves. So now we can go one step further and we can ask ourselves the question, if we now go to an experiment like this, whereby we have many small openings, not just two, which we call the double slit interference, but we have many, this many, capital N. And the separation between two openings is again that famous D, the same as it was before, except it could be much smaller if you want to make it very small. And now light comes from this direction, and now we collect it here on a screen, and this distance is L. The question is, what will you now see? And this math is more difficult. It is purely a matter of math. You now have to do a superposition of each one of these openings at any point in space and then calculate what the sum is of all these n waves. And you will find locations where there is no light, and you will find locations where there is maximum light. Now the beauty about this is, which we call gradings, the beauty about this is that if you have 100, if n is 100, then the width of that bright maximum is 50 times smaller than if you had 2. And I will demonstrate that to you. In other words, the maxima become extremely well defined. And if you use n equals 1,000, which we'll do today, then the width of the maxima shrinks by a factor of 500 in comparison with only 2 slots. And that is the great power of gradings. And I will make a sketch here of the light intensity. So this is light intensity. As you're going to see on the wall here, the wall will be here, but that's a detail. When we have a red laser and we shine a red laser through a grating. If you had a red laser and you only had 2 slits, which are this far apart, I have to keep the distance the same to compare apples and apples, then you would have seen something like this, which is what you saw there. Maximum darkness, maximum darkness, maximum darkness, maximum. But if now you do that with a grating which has, say, 6 lines instead of 2, this maximum here becomes 3 times higher, 3 times narrower, 3 times narrower, 3 times narrower, 3 times narrower, because 6 divided by 2 is 3. And for reasons that I'm not going to explain, they're 9 times higher. So they're higher and they are narrower. We give these locations a name. We call the one in the center 0 order. We call this first order, and we call this second order. And on this side, we also have first order and second order. And again, the number of maxima that you have is roughly 2d divided by lambda. I will get back to that. That's again the same idea, of course. If now you do this experiment with green light, you will see that the green light will have its 0 maximum here, because this is where the difference in path length is 0. That means the red light has its maximum, the green light, all the colors have their maximum. But you will see now that the maxima of the green light will fall here and will fall here, but there's a difference in wavelengths between red and green, and so there's a difference in the locations of those hyperboloid. But not at the zero, but here there will be differences, and then the third one would be somewhere here. And I will demonstrate that to you. So you're going to gain with a grading two things. You get more light, and you get the lines very narrow. So you get the locations of brightness become extremely well defined. And I will work with your own gradings that you have been given. Your own gradings have 13,400 lines per inch. That's what the manufacturer tells us. So your gradings have a separation between the grooves in the plastic, which is 1.9 times 10 to the minus 6 meters, 1.9 microns. You can easily calculate that if you know that 13,400 lines per inch. And so you can even make a rough guess about how many nodal lines and how many antinodal lines there are going to be. That's going to be 2d divided by lambda, and that is about 3. So you can expect then first order, second order, and third order. Well, we will do this experiment with green light and with red light. And since the wavelength of red light is larger, we will just miss the 3. We will get 2 orders in red, but in the green light, which has a smaller wavelength, you will see 3. But this is the first thing that I want to do. To have your grading, which is right here, we have your grading right here, it's the same one that you have. You will get a chance to use yours later. And we're going to show you what this interference pattern is going to be like on this screen. And you can compare it with that, which was 2 slits. Those slits were 1/4 millimeter apart. Now you have a grading whereby the separation between the grooves is only about 2 microns. But not only does that give me a larger spacing between them, but look at the wonderful how well the maxima are defined. So I'll make it dark. Make all dim in the class is probably enough. So you see how enormously well the maxima are defined. The diameter of the laser is about 3 millimeters. And so the 3 millimeters cover roughly 1,500 lines of your grading. And that's all that counts, of course, what the number of capital N is. So you use about 1,500 lines, and so that gives you a shrinkage compared to 2 lines of a factor of 750. I always carry a grading with me, no matter where I go. And I will show you now, this is the same grading that you have. I will show you now with a green laser, which has a shorter wavelength. I will do this experiment. It's the same, it's exactly the same grading, you have to take my word for it. And I will show you now that if I have a green laser, that notice that the separation between the bright green and the bright red is different, because the green has a different wavelength. The smaller wavelengths, separation is small. And if Marcos is willing to walk all the way to the right, he can show you the third order in green, but the third order in red does not exist. And so this now is an amazing tool to analyze the spectra of the various gases. When you heat them, they produce characteristic set of colors, a characteristic set of frequencies, and these can now be studied and they can be viewed with your grading. If you look at helium, you will see that it is not like the sun, that you see a continuum of all the colors, like the rainbow, but that you see very distinct lines in the helium. And the reason why we call them lines is really a misnomer, because we do these experiments with sources, light sources, which themselves are lines. And that's what I'm going to show you. And I want you to use your own gradings now. So if you get your own gradings, then I'm going to make you look through those gradings. look at a light source here, which itself is going to be a line. And if you hold your grating the right way, you have to try that a little bit, you will see this spectrum. First, you'll see zero order, where all the colors overlap. That's in the middle. You will see first order, second order, third order, maybe, depends on the color. And I'm going to make it completely dark. And then you see this amazing thing, how nature, in this case, produces unique frequencies, discrete frequencies, and no longer a continuum. And the grating is an ideal tool to see them. And try to look on both sides of the zero order so that you can see the first order. I see the first order. Wow, notice that at the zero order in the center, all the colors overlap. There's a maximum. That's zero order. But since the difference in path length is zero, of course all the colors overlap there. But then when you go to first order, you see clearly that the blue is closer to the zero order than the yellow, and the red is the farthest away. And then you see a second order, and I can even see many colors in third order, and I see the same on the left side. I can show you now neon, which is also very interesting. Oh yeah, I see clearly first order, second order, and most colors, even the most colors I see in third order. So you should now be convinced that light comes in the form of waves, as suggested by Huygens, and not in the form of particles, as suggested by Newton. And that was the goal of my talk today. However, as I mentioned earlier, I could give another talk in which I could convince you that light does not consist of waves, but that light actually consists of particles. 20th century physics has shown that light comes in the form of individual photons, and these photons can be localized in space, and we can detect them and we can count them in a similar way that you can detect and count individual tomatoes, which is a very different picture from a spherical wave moving out in all directions. We're now talking about small bullets, well localized, and you can detect them like tomatoes. So instead of throwing light photons at you, I could make an attempt to throw tomatoes at you. These are very nice. I grow them in my own backyard, and they are very soft. So if you catch them, don't squeeze too hard. You want one? Will remind you for the rest of your life what a photon is not. Ooh, good for you. I can throw some other photons to you. Here goes a photon. There goes a photon. And another photon. And for Peter, another photon. And for you there, another photon. 2 photons. Now, how can light be waves and particles at the same time? In the case of our 2-slit experiment, which was Jan did, light waves go through both slits. That's easy. You can just see that. There is no problem at all. In this picture, if light is a wave, it goes simultaneously through both. But if light is really a bullet, a photon, a particle, then it either goes through one opening or it goes through the other opening. So how can it be now that we see this interference pattern if we argue, or if we can argue, that they are also particles and bullets? And here lies now the great mystery in physics, which caused me and others sleepless nights. And the secret to this is the following. As long as you do not measure through which opening the photon went, you will see a beautiful interference pattern. The moment that you make an effort, which you can do, and you measure through which one of these openings the photon went, you have destroyed the interference pattern. You don't see the interference pattern anymore. The light says, you want me to be a particle? You pay a price for that. And this is the price that you pay. It will only show you one pile of photons here and one pile of photons there. But light says, if you don't ask through which opening I went, then that's fine. Then you behave, and then I will show you the interference pattern. And so this is a bizarreness, of course, that no one really can completely understand. And this is, of course, where quantum mechanics comes in. That is when you take 804 and 805 at MIT. And this is why I said earlier in my lecture, once you have taken 804 and 805, you have no clue anymore what light is all about. So yes, it can behave like a particle, but it can also behave like a wave, and that depends on what experiment you do and how you do the experiment. It is one or the other. And I have highlighted today only the wave character. Now I'm looking forward to seeing some of you in my classes. There is a chance that you will come to MIT, and there is also a chance that you will have me, maybe a few years from now. And then we can talk about this some more. And I want you to appreciate the fact that this is not easy stuff. Not for you, but not for me either, believe me. Thank you, it was nice having you here. When we have a current going through a wire like so, and we look at the magnetic field in the vicinity of this wire, then we know from experiment that if you put pieces of magnetite around the wire, that they line up in a circle. Put it around like this. And if that circle has a radius r, then the magnetic field, that's an experimental fact, is proportional with the current I, and it's inversely proportional with the radius of that circle. By convention, the direction of the magnetic field is given by the right-hand corkscrew. You rotate this way, the current goes up. You've seen before with electric charges, when you have a wire which is uniformly distributed, say with positive charge, you've also seen that electric fields in the vicinity of that straight wire falls off as 1 over r. Of course, the direction is different than the magnetic field, but it also falls off as 1 over r. And the reason is that electric monopoles, individual charges, the electric field falls off as 1 over r squared. And so when you integrate that out over a straight wire, you get the 1 over r field. So by analogy, it would be very plausible that if you took magnetic monopoles, that the magnetic field would also fall off as 1 over r squared. But magnetic monopoles, as far as we know, don't exist. In principle, they could exist, but we've never seen one. And if any one of you ever find one, that would certainly be a Nobel Prize. It's by no means impossible. And so the simple fact that the magnetic field around a current wire falls off as 1 over r sort of suggests that if you carve this wire up in little elements dl, that each one of those elements contributes to the magnetic field in an inverse r square law. And by integrating out over the whole wire, you then get the 1 over r field. And this is behind the idea of the formalism by Biot and Savart, who introduced the idea that if you have a little current element, dl, and the current is in this direction, and you want to know what the magnetic field is, a small contribution dB to that little current element, and the distance is r, and the unit vector from the element dl to the point where you want to know the magnetic field is r roof, then the idea is that dB, a little bit of magnetic field, in this case it would be in the blackboard, because of the right-hand corkscrew rule. Current is in this direction, so this little element would contribute to a magnetic field in this direction, perpendicular to the blackboard. It's some constant, proportional to the current, no doubt, and then it's proportional to the length of that little element dl. If it's longer, then magnetic field is larger. And in order to get the direction right, perpendicular to the blackboard, you take the cross product with the unit vector r. The unit vector r has length 1, so you only do that in order to get the direction right. And then inversely proportional to r squared. That's of course key. And this is the formalism by Biot-Savart. And you can do experiments and measure the magnetic field in the vicinity of wires, and this formalism works. So you then calculate the individual contributions of all these little elements dl, and then you do an integration, and this formalism works. You can then also measure what C is in SI units. C is 10 to the minus 7, but we write for C something quite peculiar. We write for C mu 0 divided by 4 pi. And we call this mu 0 the permeability of free space. you've seen earlier with Coulomb's law that this constant 9 times 10 to the 9th, we call that 1 over 4 pi epsilon 0, what is in the name. And so here we call this mu 0 divided by 4 pi. So now you can apply Biot-Savart's law, and you can go to a straight wire, and you have a current I, and suppose you want to know what the magnetic field at that location P is, at a distance capital R. And so what you now have to do is you carve this up in an infinite number of small elements dl, and this distance is r, and the unit vector is then like so, and you calculate the small amount of magnetic field due to this little element, and you integrate this over the whole wire. It's mathematics. You've done it. You've done it before, where we had uniformly electric charge on the wire. So I'm not going to do this again for you. It's a very straightforward piece of mathematics. The magnetic field, by the way, in this case would come out of the blackboard because of the right-hand corkscrew rule. And what you find when you do this, you will find that B equals mu 0 times I divided by 2 pi r. This being r, and so you indeed see that the inverse 1 over r comes out. And so if you, for instance, take a radius of 0.1 meters, 10 centimeters, and you have a current through the wire of about 100 amperes, then you would end up with a B field. You use this equation, 2 times 10 to the minus 4 Tesla. That is about 2 Gauss. 100 amperes, a 10 centimeter distance is only 2 Gauss. Think about it, the Earth's magnetic field is half a Gauss. So if you go 1 meter away from the wire, so you have a magnetic field which is 10 times lower, but look, it goes with 1 over r, then the magnetic field of the Earth already dominates substantially. So you need very high currents actually when you do these experiments. It's nice to see that out of Biot-Savart's formalism, the 1 over r pops out, but of course you must realize that Biot-Savart knew that the magnetic field falls off as 1 over r. That was an experimental fact. So the fact that it falls out is logical because we're cooked into that formalism. If you think about it, it all goes back to Newton. Newton was the one who first suggested that the gravitational field falls off as 1 over r squared. And then later, a logical extension was that the electric fields would fall off as 1 over r squared. And out of that came the idea that the fields of magnetic monopole, if they only existed, would fall off as 1 over r squared. And that's all behind this. And so, the person who really deserves most of the credit for all this in my book is Newton. Using Biot-Savart, we can calculate now quite easily the magnetic field at the center of a current loop. Let this be a wire, circle, and let the current go in this direction. And I would ask you, what is the magnetic field right at the center? Well, the magnetic field right at the center, of course, is pointing upwards. Each little element along the line here, dl, each little element will contribute a little bit magnetic field at that point right in this direction. And if this radius is r, with Biot-Savart now, we can calculate quite easily the total field that you would get at this location. Because that total field is then the integral of dB vectorially over the entire wire, so the entire loop. So if you go there, so you would get your mu 0 divided by 4 pi, you get your current, and you get your 1 over r squared, and now you have to do an integral over that dl cross r. Well, r is of course always perpendicular to dl. Any element dl that you choose, the unit vector r is exactly perpendicular to the element dl, because that's a characteristic of a circle. And so the sine of the angle between dl and r is 1, and so all we have to do is do an integral over dl, which is the integral of this circle, which is the circumference of the circle, and that is 2 pi r. And so now you find, you lose a pi, you lose an r, so you find mu 0 times I divided by 2r. Just to show you an example, how in this case, how easy it is to use Biot-Savart and calculate the magnetic field right at the center. If you were asked what the magnetic field was here or there, that would be also relatively easy. You've done that. I've given you a problem earlier where we had point charges uniformly distributed on a wire, and I asked you what the electric field was here. So that can also be done now with magnetic fields. If I ever asked you what the magnetic field would be here, that of course is an impossibility to do that with Biot-Savart. Practically an impossibility. I wouldn't know how to do that. But in principle it could be done, and certainly with a computer you can do it. So we can go to our same situation. We can take 100 amperes for I, and you can take R 0.1 meters, and then the B field, the strength of the B field right at the center of this loop that I found is then 6 times 10 to the minus 4 Tesla. And that would be 6 Gauss. It's clear that if you want to put in some field lines, magnetic field lines, as a result of this current going around in a circle, that through the center there would be a field line like so. If you're very close to the wire here, which goes into the blackboard, I want you to see this three-dimensionally, then a magnetic field would go like this, clockwise. Here the current comes to you, so it would be counterclockwise. And if the magnetic field line is here like so, and here it is curled up, then clearly I expect them to be here, sort of like so, and like so, and like so. So this is the kind of magnetic field line configuration that I would expect then in the vicinity of such a current loop. And I want to show this to you in a little bit more detail. I have here a transparency, and you see there on the right side the current goes into the paper, and here it comes out of the paper. It is a circular loop, and you see here the field line configuration. It's not too different from what I have on the blackboard there. Very close to the wires, of course, you get circles, because the 1 over r dominates there. You're so close to the wire that the 1 over r relationship makes it come out like circles, and here too, but then if you're farther away you get configurations like I have there. When you're very far away from a current loop, the magnetic field configuration is very similar to that of an electric dipole. I can show you that in the following way. Let's first look at the electric dipole that you see up there. This is a positive charge, this is a negative charge. Don't look anywhere near the charges, don't look in between the charges. Look far away. Here you see electric field lines. You see them here. Now look at your current loop here. The current is going into the paper here, coming out of the paper. It is a loop. And look, you see the same configuration. Field lines. Field lines. This goes like so. This one goes like so. Here, the electric field lines coming in. Magnetic field lines are coming in. Electric field lines are going out. Magnetic field lines are going out. They look very similar. Gauss' law tells me that the closed surface integral of the electric flux is the charge inside the box divided by epsilon zero. And so if you have a closed surface here, it looks like a line, but I meant it to be a surface, then that closed surface integral of the electric flux is not zero, because there's a charge inside the box. No matter where in the magnetic field you make a closed surface, there is never any magnetic flux going through that surface. Never. Unless you come into 26100 and show me a magnetic monopole. Only then will there be magnetic flux coming out of a closed surface. If we put the magnetic monopole inside. And this now brings us to the second of 4 Maxwell's equations. The first one being Gauss' law. The second one is that the closed surface integral of B dot dA is always zero, unless you come with a magnetic monopole. So we now have 2 of Maxwell's 4 equations in place. Historic day. I want to show you the magnetic field in the vicinity of a wire like this. I have to use a few hundred amperes through that wire. I told you why, because magnetic field falls off quite rapidly. And I do that with iron file, which I will sprinkle around the wire, and these magnetites will orient themselves in that magnetic field. And then I will try to also make you see this field configuration by having one wire going into the paper and one coming out of the paper. So let's first look at the single current wire. It's coming towards you and it goes into, of course. It is a wire that goes like this, and the reason why you see it here is, of course, we have to get the current in somehow. But it really is a wire like this. And this platform I'm going to show you. So I'm going to put some iron file around this. These are magnetites, and when they see a magnetic field, they will try to orient themselves in the direction of the magnetic field. So you're going to see these circles. But appreciate the fact that you need huge currents for this. Hundreds of amperes we do. That's why we have a car battery here. Remember, that was capable of delivering many hundreds of amperes. So I close the current now. I tap, and you can see the circular configuration. I hope you can see that. It looks like circles. I want to do the same now, which is a little bit more exciting perhaps, with one wire going into the plane and the other one coming out. Even though it's not a circle, the idea is that you get a field configuration very much like you see there. Oh, it's already hot. These cables are already hot. They don't like the few hundred amperes. Okay, let's do it this way. So you're going to see a field configuration similar to what I have on the blackboard, similar to what you have here. Oh no, not this one. Similar to this. Yeah, actually it was also the one I had, but this is a nicer way to look at it. So we have one wire going in and one wire coming out of the plane. All right, so let's first put some iron file on. All right, and now a few hundred amperes through it. Tap it, and you can see close to the wires that goes in, here and here, you see circles, because of the 1/r relationship. They dominate the magnetic field. But look in between here, with a little bit of imagination, you can see these field lines going like this, just like I have there on the blackboard. All right. We don't need this anymore, and we don't need that anymore. So this gives you a little bit of insight into the magnetic field configurations that we have about these wires when we run a current through. I will return to magnetic fields next lecture, and we will expand on it. We will learn techniques to calculate magnetic fields in a way which is highly superior to Biot-Savart's law. In fact, that will get us to the third Maxwell equation, almost. But I now want you to relax a little bit, because this may already have been a little rough on you. And so now I want to discuss something entirely different, something very practical, and that has to do with the transport of electric energy. So we have a power station somewhere at location A, and they deliver electric power, electric energy to Boston. Here is Boston, location B. And A is the location of the power station. This could be 1,000 miles, the distance. There's a cable going from the power station to us. And the potential here in this line is V of B. And here's a cable for the return current, so the current goes like this, and the return current is in this direction, and here you use this energy. You hook up your computer, you hook up your hairdryer, your heaters, electric toothbrush, and what have you, your TV station, everything. And so you are the consumer here. You take the energy that is provided by this power station. I will call the potential of this line 0, and so this is V of A higher than this line here. Well, according to Ohm's law, VA minus VB is the current times capital R, which is now not radius, but that is resistance in the wire. This wire, this cable, however thick it may be, has a finite resistance. And so VB, that is the potential that we receive in Boston, equals VA minus IR. So if there's no current going through the wire, no one is using any electric energy, then VB is the same as VA. Now I want to know if we consume energy, so we're dealing now with power. So the power that we take off at Boston is I times V of B. That's the number of joules per second that we are consuming. So that then equals VA times I minus I square R. That's fine. What is this? This is the energy per second that we are consuming. What is this? This is the energy per second that the power station is delivering to us. What is this? That's lost energy. It's the I square R, it is the heat produced in this cable. It goes into the universe, it's gone. So the economy demands that we try to make this as small as possible. See, this is the power that is available, but you get a loss of power in terms of heat, the minus sign here. So you get less in Boston. And so how can you make this I square R low? Well, what is the resistance of a wire? That is rho, which is the resistivity, times the length of the wire, divided by the cross-section of the wire. So you have several options. You could make A very large, a very thick copper wire. That's expensive. You could also make the wires out of gold that has a lower resistivity than copper. That's also expensive. People are thinking of making these transmission wires of superconducting material. They have to cool them at very low temperatures. That's outrageously expensive. But that's a way you could get the resistance down. Let's now look at the current. What can we do with the current? Suppose we consume 100 megawatts, not an unreasonable number. So we are consuming 100 megawatts. And just for the sake of the argument, suppose at VB the potential is 100 volts. So V of B is 100 volts. What now is the current? Well, current times potential gives me power. And so my current is now 1,000,000 amperes. Alternatively, suppose that the potential at B in the wire is 100,000 volts. 1,000 times higher. Now the current is only 1,000 amperes. Gives me the same power. In both cases, am I consuming at a rate of 100 million joules per second. But I square R, the heat loss on the way from the power station to me, is 1,000,000 times lower in this case than in that case, because I is 1,000 times lower. And the heat loss goes with I squared. And so now you understand why electricity, when it is transported from one place to another, why is it done at the highest voltage possible. When you get to Boston, you obviously got to do something about this enormous potential, because if you were to deliver 100,000 potential difference there, then half the population in Boston would electrocute itself. So now you got to come down in voltage, which you do with transformers. We will talk about that later in the course. And so you bring it down to a comfortable voltage, which is in the United States about 110 volts. In Europe it's 220. So now comes the question, how high can you make V of A? The higher you could make it, the less loss there would be along the way. Well, you got to stay away from the breakdown electric field, which is the 3 million volts per meter. If at the surface of these cables you get 3 million volts per meter, you get corona discharge. That's a big loss. You want to stay away from that. And so typical cables have about a radius R. This is now, R is the radius of the cable of about 2 centimeters. That gives them a cross-sectional area, I think of about 10 to the minus 3 meters squared, that's correct. And the potential V at A is roughly 300 kilovolts. And with that configuration, you stay comfortably below the electric field of 3 million volts per meter. So you don't get the corona discharge. If the length of that cable, L, if that were something like 1,000 kilometers, not an unreasonable number, 1,000 kilometer distance from, if we get our electricity from the Niagara Falls to Boston, not an unreasonable number, you can calculate now what the resistance of that cable would be. Because that resistance R equals rho times L divided by A. If you take copper, that has a resistivity of 2 times 10 to the minus 8 SI units. We have a length of 10 to the 6 meters of the cable, and we have a cross-sectional area of 10 to the minus 3 square meters, so that 1,000 kilometer cable would only have a resistance of 20 ohms. And to make the numbers a little easy, if we have a current, say, of 300 amperes, then the power that the power station produces, if we take the 300 kilovolts for now, that power would be the 300 kilovolts times the 300 amperes, and that is about 90 megawatts. That's close to my 100 that I had in mind earlier. So you can calculate now what the loss is. The loss is I squared R. You know R is 20 ohms. You know I is 300 amperes. And so you'll find now that you have about 2 megawatt loss. That's not bad. 2 out of 90. So you have about 2% energy loss in transportation. You can also calculate now what the difference is in potential between the power station and Boston. VA minus VB is IR. You know that I is 300 amperes, and you know that R is 20 ohms. So VA minus VB is about 6 kilovolts. In other words, if the power station puts it on the line at 300 kilovolts, then you would get it here with only 6 kilovolts less. So it's not a very unreasonable situation. I told you that these power lines have to stay away from the 3 million volts per meter electric field, because then you get corona discharge. And when there is thunderstorms in the area, it can actually push up the electric field on the wire, and you can get corona discharge. I have seen that several times. Not only seen it at night with my naked eyes, that you see the power lines glow, but I've also heard it, because you can hear this cracking noise of corona discharge. It's very fascinating, actually. I have a slide here which shows that. So here you see a high voltage power line, transmission line, and you clearly see the glowing of the corona discharge. They compare that with what's called the Roma's kite string. Kite strings at night, when you fly them near thunderstorms, can also produce corona discharge and light. That's why they call Roma's kite string candles. Benjamin Franklin did quite a bit of experiments at night with kites near thunderstorms. Dangerous business, by the way. So you see that these high voltage power lines can go into a corona discharge. I now want to revisit our Leyden jar. We had a truly absurd situation whereby we did an experiment with a jar which you still see here, and I will redo the demonstration, but it's crying for an explanation because it looked like there was something wrong with physics. And I want to refresh your memory of what we have seen before and what this Leyden jar is all about. The Leyden jar is nothing but a capacitor with a dielectric between two conductors in the shape of a bottle, of a jar. And so the inner portion, which is glass, say has this shape. You see it there. You're going to see it shortly there. And then we have conductors, a conducting beaker around it here. And we have a conducting beaker on the inside. And we charge this up with the Wimhurst. This is the Wimhurst machine. And when we do that, we get free charge on the conductor. And so you get sigma free right here, and you get it here. Opposite signs, of course. And you get sigma induced on the dielectric. Why do you get it? Because the dielectric sees an external field due to this sigma free. And so it begins to polarize. And so you get here induced charge, and you get there induced charge. If this side is positive, then the induced charge here will be negative, and vice versa. We have here a metal hook so that we can lift out the inner portion. So what we did, we charged it up with the Wim Hof, and then there is a certain amount of energy. The electrostatic potential energy of this configuration is 1/2 Q free times the potential difference, and the Q free is the charge which is on the outer conductor. And what I then did, I disassembled it very carefully after we had charged it up, took the inner portion out, took the glass out, the outer portion, and I took all the free charge off. I touched the conductors and discharged them. So there is no Q free left, gone. The moment that that is gone, the induced charge must also go away, because the induced charge is only there because of the free charge. Remember, the induced charge density is 1 minus 1 over kappa times sigma free. So if glass has a kappa of 5, then the induced surface charge density is about 0.8 times the free surface charge density. The moment that the free one goes, the induced one goes. And then I assembled it again, and much to our surprise, when I short out the inner portion with the outer portion, we saw a huge spark. That means there was energy left. And that is very puzzling. There cannot be any energy left unless there's something wrong with physics. So I first want to show that again to remind you of what you have seen before, and then I will make a proposal for an explanation. And let me check my light configuration. Oh, we're going to make it all dark. I can charge it up while you're seeing it, actually. Yeah. Make it dark now. And now I will disassemble it. I take the inner portion out. The glass is a good insulator, so I don't mind touching that with my hand. Okay, and so now I take the inner conductor, touch it, lick it, kiss it, take all the charge off, there it is. Do the same with the outer conductor, have it in my hand. For sure there is no Q free left anymore, on that anymore. I put the glass back in again, and then I put the inner core again. And now I'll make it a little darker for you, because I want you to see that when I short this out, that you're going to see a spark. So I'm going to turn the light down. So look very closely. I'll tell you when I'm going to do it. 3, 2, 1, I'm approaching it now, 0. And there's a huge spark. That means energy. And that's crazy. There shouldn't be any. And so some of you must have had sleepless nights, not being able to explain this. Some of you actually wrote me email. You didn't have sleepless nights, I can tell that. So what's going on? There's only one possibility, and that is there must be free charge on the glass. How did it get there? Well, corona discharge. That's the only way it can get there. Keep in mind that the electric field in air, E in air, can be no larger than 3 times 10 to the 6 volts per meter. If it gets larger, you get corona discharge. In glass, by the way, it's a bit higher. It's 10 to the 7 volts per meter. I will now make some calculations based on certain assumptions. And those assumptions may not be exactly accurate, because I don't know the exact dimensions of this system, but the exact dimensions don't matter. What matters is the idea behind it, why it does such crazy things. So first of all, I will assume that this capacitor is just two parallel plane plates. That's a simplifying situation because it has the shape of a bottle. I will assume that the Wimshurst produces about 30 kilovolts. I know that it's approximately right, but it may be 25. It may be 35. I will assume that the air gap between the outer conductor and the glass is 1 millimeter, that both are 1 millimeter. And I will assume that the glass thickness is 3 millimeters, and I take kappa equals 5 for the glass. So that is the basis of my calculations. So now I have here the conductor on the outside, this is the glass, and this is the conductor on the inside. So this is 1 millimeter thick, this is 3 millimeter thick, and this is 1 millimeter thick. And the potential difference over the whole thing is going to be 30 kilovolts. But I know that the potential difference is always E times D. That holds for this gap, the local E times this D, the local E times this D, and the local E times that D. I also know that E glass is the same as E in the air divided by that kappa, which is 5. And I know that the total potential difference between here and here must be 30,000 volts. And so this allows me now to calculate in a very straightforward way the electric field here in the air, the electric field here in the air, and the electric field in the glass, because I get a simple equation with one unknown. And that's the following. I first go over this gap, and so I get E in the air times that distance, D, which is 1 millimeter. But of course later on, I have to go through this gap again, so I'll multiply it by 2 now. And now I have to add the electric field in the glass, which is the same as air divided by 5, times its distance, which is 3 millimeter. And that must now be 30,000, because that's the potential difference between here and there. That's one equation with one unknown. And I can calculate the electric field in the air gap. And the electric field in the air gap turns out to be 11.5 times 10 to the 6 volts per meter. It's here the same, of course, 11.5 times 10 to the 6. And here it is 5 times smaller. So I find here 2.3 times 10 to the 6. To show you that I did my homework correctly, the potential difference here is now 11.5 kilovolts. I put it here in kilovolts. The potential difference here is now about 7 kilovolts. And the potential difference here is the same, is 11.5 kilovolts. And if you add them up, you get 30. If you look at this cannot be, because a field of 11.5 times 10 to the 6 is way above the breakdown electric field. And so what is going to happen? You're going to get corona discharge from the conductor to the glass. And so what you're doing is you're spraying charge on the glass. And that's the key to the solution of this bizarre behavior. And so when you later disassemble it and you take the free charge of the conductors, there is still this free charge which you have sprayed on the glass. I never removed that. It's very hard to remove because the glass is an insulator. It's very difficult to take charge of an insulator. It's easy to take it off a conductor. But I never even attempted that, because I made you believe, as I believed myself for years, that once you take the Q-free of the conductor, that there can be no charge on the glass. That is wrong, because there is corona discharge. So now comes the question, before we disassemble, what now is the configuration of the electric fields and the potentials. I'll make a drawing here. And so now I draw again the conductor, the glass, and the conductor. I'd assume now that after the corona discharge, this field here is 3 times 10 to the 6. Maybe a little lower, but that's the maximum it can be. And so the field here in the air will be also 3 times 10 to the 6 volts per meter. But since I know that the potential difference between here and here must be 30 kilovolts, I can now immediately conclude that the electric field here is now 8 times 10 to the 6 volts per meter. That is the only way that it adds up to 30 kilovolts. Because the 3 million volts per meter gives me here 3 kilovolts. This here gives me 3 kilovolts. So now I need a potential difference here of 24 kilovolts. And that over 3 millimeters requires this field. Look, this field is stronger than that field. Whereas earlier we made the assumption that this field was 5 times lower than that field. Yeah, why is it now higher? Because we have sprayed right here on this surface, we have sprayed free charge. It's no longer the field that is dictated by the external field and then the induced charges. That's no longer the case. It carries now itself free charge. You now have all the tools, maybe not the courage, to calculate how much free charge there is right here on the glass to get this field. It's a very straightforward calculation. And you will find that there is 12 times more free charge here on the glass than there is here on the conductor. 12 times more. And so if I disassemble and remove the free charge on the conductors, I have almost done nothing, because most of the free charge is on the glass, and I have not touched that. So now, if I reassemble, I have almost all energy left. I have not lost much. Lost some, but not much. And so what I should really have done, I should also have discharged the inner glass. That's not easy, but I will try that today. It's not easy because it's very hard to take that charge off. But I will try that. And then, there shouldn't be much energy left if we reassemble it again and try to get a spark out. So I go through the same routine. I'm going to charge it up now. Okay. Take this cable off. Take that cable off. I take it apart. Do everything that I did before, the same way. Gone, all charge gone, whatever there was, all charge gone. Now this is more difficult. This is not enough if I do this. I have to get in there. Oh, I can actually feel it. It's a great feeling. I can feel sort of a corona discharge with my, I have to really get everything out. And that's not easy. It's not. In fact, when I rub in with my shirt, I may even make it worse. I may be charging it up through friction. But I'll do the best I can. That's very indecent what I'm doing. Okay. So I try to get the charge now, something that we ignored completely before. This is really where the energy was. And I'm trying to kill that now. And so now I'm going to reassemble it. And I'll go through the same routine. Good thing I didn't break it. Put it back in again. I'll make it dark, so that you can see whether perhaps there may be a little bit of spark if I didn't succeed to remove all the charges from the glass. So I'm going to short it out again. 3, 2, 1, 0. And I saw a teeny little spark. You may not even have seen it. So you have to conclude now that the physics behind this lies in the glass, and physics works even when it sometimes surprises us. See you Wednesday. All physics of the 19th century and earlier is called classical physics. Examples are Newtonian mechanics, which we dealt with this whole term, and electricity and magnetism, which you will encounter the next term. In the early part of this century, when we learned about the composition of atoms, it became clear that classical physics did not work on the very small scale of the atoms. The size of an atom is only 10 to the minus 10 meters. If you take 250 million of them and you line them up, that's only 1 inch. In 1911, the English physicist Rutherford demonstrated that almost all the mass of an atom is concentrated in an extreme small volume at the center of the atom. We call that the nucleus. It's positively charged. And there are electrons, which are negatively charged, which are in orbits around the nucleus. And the typical distances from the nucleus to the electrons is about 100,000 times larger than the size of the nucleus itself. As early as 1920, Rutherford named the proton, and Chadwick discovered the neutron in 1932, for which he received the Nobel Prize. Now let us imagine that this lecture hall is an atom. And the size of an atom is defined by the orbits, the outer orbits of the electrons. If I scale it properly now, in this ratio 100,000 to 1, then the size of the nucleus would be even smaller than a grain of sand. And it just so happened that yesterday I went to Plum Island, I walked for 3 hours on the beach, and I ended up with some sand in my pocket. And so I will donate to you 1 proton. Make sure you hold on to it. Ooh, that is 2 protons. That's too generous. So keep it there. This is 1 proton. To think about what an atom is. An atom is all vacuum. You and I are all vacuum. You think of yourself of being something, but we are nothing. You can ask yourself the question, if you're all vacuum, why is it then that I can move my hand, not through the other hand, like a ghost can walk through a wall? That's not so easy to answer. And in fact, you cannot answer it with classical physics, and I will not return to that today. But you are all vacuum. According to Maxwell's equations, Maxwell's law of electricity and magnetism, an electron, because of the attractive force of the proton, would spiral into the proton in a minute fraction of a second. And so atoms could not exist. Now we know that's not true. We know that atoms do exist. And so that created a problem for physics. And it was the Danish physicist Niels Bohr who in 1913 postulated that electrons move around the nucleus in well-defined energy levels, which are distinctly separated from each other, and that the spiraling in of the electrons into the nucleus does not occur for the reason that an electron cannot exist in between these allowed energy levels. It can jump from one energy level to another, but it cannot exist in between. Now Bohr's suggestion was earth-shaking, because it would also imply that a planet that goes around the sun cannot orbit the sun just at any distance. You couldn't move it just a trifle in or a trifle farther out. It would also require discrete energy levels. It would also mean that if you had a tennis ball and you would bounce the tennis ball up and down, that the tennis ball could not reach just any level above the ground, but it would only be discrete levels. And that is very much against our intuition. We'd like to think that when you bounce a tennis ball, that it can reach any level that you want to. You give it just a little bit more energy, and it will go a little higher. That, according to quantum mechanics, would not be possible. Now, all this seems rather bizarre, as it goes against our daily experiences. But before we dismiss the idea of quantization, you see, the quantization comes in when you talk about discrete energy levels, you have to realize that the differences in the allowed heights of the tennis ball and the differences between the allowed orbits of the planets around the sun would be so infinitesimally small that we may never be able to measure it. In other words, quantum mechanics really plays no role in our microscopic world. Now, atoms are very, very small compared to tennis balls, and the quantization effects are much larger in the submicroscopic world of electrons and atoms than in our familiar world, baseballs, pots and pans, and planets. So before we continue, I would like to repeat to you one of the cornerstones of quantum mechanics. And it says that the electrons in atoms can only exist at well-defined energy levels, and they cannot exist in between. Now, when I heat a substance, the electrons in the atoms can jump from low energy states to high energy states. And when they do so, they can leave a hole, an opening, an empty energy state. But later on, they can fall back to fill that opening. They can occupy that energy state again. And when I keep heating this substance, there is some kind of a musical chair game going on. The electrons will go to higher energy levels. They may spend there some time, and then they may fall to low energy levels. You see here a vase, a very precious vase. And when I pick up this vase, I have to do work. I bring it further away from the center of the Earth. Now, is that energy lost? No. I could drop the vase, and it would pick up kinetic energy. I will get that energy back. Gravitational potential energy will be converted to kinetic energy. It will crash to pieces, and it will generate some heat. In fact, the breaking itself of this vase would take some energy. In a similar way, the energy that you put into electrons when you bring them to higher energy levels is retrieved when the electrons fall back. So there is a parallel. Dropping this vase and getting the work back that I put in. That wouldn't be a nice thing to do to this 500-year-old vase. But as far as I'm concerned, perfectly reasonable to do it with Ohanian. So we can let that go, and the energy will come out in the form of heat and also in the form of perhaps some noise. When electrons fall from higher energy states to low energy states, it's not kinetic energy that is released, but it comes out often in the form of light, electromagnetic radiation. Light has energy. Einstein formulated that a light photon, the energy of a light photon, is h times the frequency, and h is Planck's constant, named after Max Planck, and h is about 6.6 times 10 to the minus 34 joule seconds. Now, we've also seen in 801 that lambda, the wavelength of light, equals the speed of light divided by the frequency. And so if I eliminate the frequency, I also can write that the energy of a light photon equals hc divided by lambda. And so you see, the more energy there is available, the smaller the wavelength. The less energy there is available, the longer the wavelength. And so if the jump from a high energy state to a lower energy state is very high, then the wavelength will be shorter than when the jump is relatively small. I can make you some kind of an energy diagram of these jumps. And these are energy levels, so energy goes in this direction. This would be the lowest possible energy state. So these would be allowed energy levels, allowed orbits. And if this electron had jumped all the way here, then it could fall back at a later moment in time, and the energy could be so much that you couldn't even see the light. It could be ultraviolet. And this jump may still be ultraviolet. But now this jump, which is a little less energy, that may be in the blue part of our spectrum. So we may see this as blue light. And this one, which is a little less than this energy, this jump may generate green light. And the jump from here to here, which is even less, may generate red light. And the jump from here to here, which is even less, may again be invisible. So this may be infrared. And so as the electrons fall from a high energy state to a lower energy state, you expect very discrete energies to come out, very discrete wavelengths. And these wavelengths that you would see correspond then to these allowed transitions between these energy levels. So if we could look at that light and sort it out by color, we would in a way see these energy levels. Now, you have in your little envelope a piece of plastic which we call the grating, and the grating has the ability to decompose the light in colors, which we call a spectrum, and we're going to shortly use that grating to look at light from helium and light from neon. But before we do that, I'd like to hand out as a souvenir to a few people, randomly picked, something that they can also use. It's not as good as your grating though, but it is also nice. You will see a more spectacular result, but not as clean. It's not as clean. All right, one for you, one for you, one for you, and one for you. And you want one, I can tell that, and you want one. And here. Two for you. For you. Oh no, this side hasn't had anything. I gotta walk all the way over now. So this is really for children's parties, which I'm handing out. Whereas, oh, George Coster, you want one, of course. Professor Coster wants one. I couldn't bypass him. And you want one. Okay, and you want one. So, by all means, use your grating. But then at the very end, you can always use these little spectacles, which don't work nearly as well, but this kind of thing. I'm going to light here this bulb, this light, which has helium in it. And what you're going to see with your grating, if you hold your grating properly, you may have to rotate it 90 degrees. You will see how that works when you try it. You're going to see very, very sharp, narrow lines at various colors. I want you to realize that the reason why you see very sharp, narrow lines is only because my light source, a very sharp, narrow line. If you use it on something that is not a very sharp, narrow line, then you're not going to see through that grating very sharp, narrow lines. So don't confuse the lines that are on the grating with the line source that I have here. Now when you look through your grating very shortly, you will see on both sides the wonderful lines. It's a mirror image, and we will discuss it in a little bit more detail. But before you look through your grating, I first want you to simply look at it without the grating. Because then it is even more spectacular when you lose the grating, because you have no clue when you don't use the grating what kind of colors are hidden there. And the colors that you're going to see are these electron levels. So I'm going to make it dark. And I will turn this on. And this one, I believe, is helium. I have a grating here. So you have to rotate it so that you see vertical lines on either side. You may have to rotate it 90 degrees, no more. And if you look closely, for instance, look on the right side of the light, you will see a distinct blue line, a few blue lines, green, very nice bright yellow one, and you see red. And if you go further to the right, you see a repeat. It's a little fainter, but you see a repeat of that. That's not important right now. I just want you to see that this light, which you have no idea that it comes out in very discrete wavelengths, very discrete frequencies, and they correspond to these jumps from allowed energy levels to other allowed energy levels, but there's nothing in between. And when you look on the left side, you'll see a mirror image of what you see on the right side. Now helium has only 2 electrons. And now I'm going to put in a neon bulb, and that makes it richer for reasons that neon has 10 electrons. So you have many more allowed energy levels, so many more ways that the electrons can play musical chair. A lot of lines in the red. I'm not blocking you, I hope. A lot of lines in the red and some beautiful lines in the yellow. I see some in the green. I don't see much in the blue. Yeah, a little bit in the blue. But the key thing is, I want you to see that these lines are discrete. It is not just any wavelengths that can be generated. It's only the allowed energy levels, the musical game, when the electrons jump from one orbit to another. And that gives you this unique discrete spectrum. Now, these line spectra were known long before Bohr came with his daring ideas, but before quantum mechanics, these lines were a great mystery, but they no longer are. I suggest you use this grading and use it when you're outside at night, look at some street lights, particularly sodium lamps and mercury lamps, and of course the neon lamps are quite spectacular. But keep in mind, you will not see very nice straight lines unless your light source itself has very nice, straight, narrow light source. Now, quantum mechanics took a big leap in the 20s, and it would be impossible for me in the available amount of time to do justice to all the basic concepts. However, I will discuss some consequences that are rather non-intuitive. Prior to quantum mechanics, there was a long-standing battle between physicists whether light consists of particles or whether they are waves. Newton believed strongly that they are particles, and the Dutchman Huygens believed that they were waves. And it seemed like in 1801 that a conclusive experiment was done by Young, which demonstrated unambiguously that light was waves. Huygens was right. But as time went on, discomfort was growing, as there were also experiments that showed rather conclusively that light really was particles. And it was one of the great victories of quantum mechanics that it showed that light is both. At times it behaves like waves, and at other times it behaves like particles. It all depends on how you do your experiment. In 1923, Louis de Broglie made the daring suggestion that a particle can behave like a wave. And he specified, it was very specific, that the wavelength, which nowadays is called the Broglie wavelength, is h, Max Planck's constant, divided by the momentum of that particle. And the momentum is the mass of the particle times the velocity, as we have seen in 801. If the momentum is higher, then the wavelength is shorter. A baseball will have a very high momentum with a ridiculously low short wavelength. Now, one of the startling consequences is that protons and electrons, which everyone at that time considered particles, can then also be considered as being waves. And in 1926, the Austrian physicist Schrödinger drove the nail in the coffin with his famous equation, Schrödinger's equation it's called now, which is the ground pillar of quantum mechanics, and it unifies the wave and the particle character of matter. Returning to my baseball, take a mass of the baseball of, say, 0.5 kilogram and give it a speed of 100 miles per hour. Calculate the wavelength that you would find, according to quantum mechanics. That wavelength is so absurdly small, so it is completely meaningless. So quantum mechanics plays no role in our microscopic world of pots and pans and baseballs. But now take an electron. You take the mass of the electron, 10 to the minus 30 kilograms, and you give the electron a speed of, say, 1,000 meters per second. Now you get a wavelength which is comparable to the wavelength of visible light, red light. Now something that becomes very meaningful, something that can be measured. Now you may argue, gee, what difference does it make? Who cares whether something is a wave or whether something is a particle? Well, it makes a huge difference. Because waves have crests and they have valleys. And so if you take two sources of waves, either water waves, two sources, tapping up and down on the water, or you can take two sound sources, then there are certain locations on the surface of the water where the crest of one wave arrives at the same time as the valley of the other. And so they cancel each other out. There is nothing, there's no motion of the water. We call that destructive interference. Of course, there are other places where there is constructive interference, where they support each other. Now, if particles can do that too, that is very hard to imagine. How can one particle with another particle interfere and vanish, that the two particles no longer exist? So if indeed particles are waves, you should be able to demonstrate that by having the interference pattern of two particles like the water waves and make at certain locations in space those particles disappear, which turned out to be possible. But that's a very non-intuitive idea. So we think of it too classically when we say, well, two particles cannot disappear. But in quantum mechanics, you can think in waves if you want to, and then you have no problems with the interference pattern and the destructive interference at certain locations. Now, there are other remarkable consequences of quantum mechanics in classical mechanics. If you and I are clever enough, you think that we should be able to determine the position of an object to any accuracy that we require, and at the same time determine also its momentum at any accuracy that we require, just a matter of how clever we are. Simultaneously, the object is right there, and that is its mass, and that is its speed. However, the German physicist Heisenberg realized in 1927 that a consequence of quantum mechanics is that this is not possible. Strange as it may sound to you, Heisenberg stated that the position and the momentum of an object cannot be measured very accurately at the same time. And I will read to you Heisenberg's uncertainty principle, the way we know it. It says the very concept of exact position of an object and its exact momentum together have no meaning in nature. It is a profound non-classical idea, and it is hard for any one of us, you and me included, to comprehend. But it is consistent with all experiments that we can do to date. I want to repeat it because it's going to be important of what follows. The very concept of exact position of an object and its exact momentum together have no meaning in nature. What does it mean? First, let me write down Heisenberg's uncertainty principle. Delta P, which is the uncertainty in the momentum, multiplied by delta x, which is an uncertainty in the position of that particle, is larger or approximately equal to Planck's constant divided by 2 pi, for which in physics we call that h bar, and h bar is approximately 10 to the minus 34 joule seconds. You see h is 6.6 times 10 to the minus 34. If you divide that by 2 pi, you get about 10 to the minus 34. What does this mean now? What it means that if the position is known to an accuracy delta x, we'll give you some examples, that the momentum is ill-determined, is not determined to the amount delta p larger or equal than h bar divided by delta x. That's what it means. And I'll give you an example which I've chosen from a book of George Gamow. Gamow wrote a book which he called Mr. Tompkins in Wonderland. It's about dreams. Mr. Tompkins wants to understand the quantum world. And there is a professor, you will see a picture of the professor, who takes him in his dreams along the various remarkable, non-intuitive effects of quantum mechanics. And in one of these dreams, the professor suggests that we make h bar 1. And the professor takes a triangle on the pool table, and he puts the triangle over one billiard ball. So the billiard ball is constrained in its position, and that delta x is roughly, say, 30 centimeters, 0.3 meters. That means that the momentum is not determined to an approximate value of 1 divided by 0.3 is about 3 kilogram meters per second. Now, if we give the billiard ball a mass of 1 kilogram, then delta P is m delta V. And so if m is 1 kilogram, then the speed of that billiard ball is undetermined, according to Heisenberg's uncertainty principle, by at least approximately 3 meters per second. 3 meters per second, that means 7 miles per hour. And so that billiard ball will go around like crazy in that triangle. And that's exactly what happens in the dream. And I will show you here a picture from that book. Mr. Tompkins is always in pajamas, just to remind you that it is a dream. And needless to say, the professor is a very old man and has a very nice beard. Adds to the prestige. And I will read you from this book. I will read you a very short paragraph that deals with this. So the professor says, look here, I'm going to put definite limits on the position of this ball by putting it inside a wooden triangle. As soon as the ball was placed, in the enclosure of the hole inside of the triangle became filled up with glittering of ivory. You see, said the professor, I defined the position of the ball to the extent of the dimensions of the triangle. This results in considerable uncertainty in the velocity, and the ball is moving rapidly inside the boundary. Can't you stop it? Asked Mr. Tompkins. No. It is physically impossible. Any body in an enclosed space possesses a certain motion. We physicists call it zero-point motion, such as, for example, the motion of electrons in any atom. So here you see quantum mechanics at work when h bar is 1. This is a very non-classical idea, because you and I would think, and we've always dealt with that in 801, that you can take an object and place it at location A, and we say at time t0 it is at A and it has no speed, and we know the mass. So we know both the momentum and the position to an infinite accuracy. But according to quantum mechanics, that's not possible. So let's now return to the real world, where h bar is not 1, but where h bar is 10 to the minus 34. And let's now put a billiard ball inside this triangle. Now, delta x is the same, but since h bar is 10 to the minus 34, delta p is of course 10 to the 34 times smaller, and so the velocity is 10 to the 34 times smaller. This undeterminedness, degree to which the velocity is now undetermined, is so ridiculously small, it is 3 times 10 to the minus 34 meters per second, that if you allowed that ball to move with that speed, in 1 billion years, it would move only 1/100th of a diameter of a proton, so it's meaningless again. And so again you see that quantum mechanics plays no role in our daily microscopic world of baseballs and basketballs and billiards and pots and pans. And therefore it is completely okay for us to say, I have a billiard ball which is at point A and its mass is 1 kilogram and it has no speed. That is completely kosher, completely acceptable, and quantum mechanics has no problems with that. Let's now turn to an atom. Take a hydrogen atom. The diameter of a hydrogen atom is about 10 to the minus 10 meters. So the electron is confined to a delta x of about 10 to the minus 10 meters. That means the momentum of that electron becomes undetermined, according to Heisenberg's uncertainty principle, to about 10 to the minus 34 divided by 10 to the minus 10 is about 10 to the minus 24 kilogram meters per second. What is the mass of an electron? That's about 10 to the minus 30 kilograms. So this, delta P, is also m delta V. So it means that delta V, that means the velocity of the electron, is undetermined, according to Heisenberg's principle, by an amount which is at least 10 to the minus 24, which is this delta P, divided by the mass of the electron, which is 10 to the minus 30. And that is about 10 to the 6 meters per second. That is 1/3% of the speed of light. So the electron is moving only because of the fact that it is confined. That's what quantum mechanics is all about. The electron's motion is dictated exclusively by quantum mechanics. I'm going to show you an experiment in which I want to convey to you how non-intuitive Heisenberg's uncertainty principle is. I have here a laser beam, and this laser beam is going to be aimed through a narrow slit. I'll make a drawing. I'll turn this light off. And that slit, which is a vertical slit, can be made narrow and can be made wider. Here is this light beam, and here is this opening, this slit. It's only going to be confined in this direction, not in this direction. So the light will come out here, and then on a screen, which is going to be that screen, the large distance, capital L, we're going to see that light spot due to the light beam going through the slit. And this separation, capital L. I start off with the slit all the way open. And so you're going to see this light spot like this. And then I'm going to make the slit narrower and narrower. And as I'm going to cut into the light beam, what you're going to see is exactly what you expect. You expect that this light disappears, and when I cut in further, you see exactly what you expect, that this light disappears. And so the light spot there on that screen will become narrower and narrower and narrower. But then there comes a point that Heisenberg says, careful now, because your delta x, your knowledge, the accuracy in this direction where the light goes through is now so high that now I'm going to introduce an uncertainty in the momentum of that light. The momentum of that light is now no longer determined to infinite accuracy. And what that means, if you start fooling around with the momentum of that light in the x direction, it no longer goes through straight, but it goes off at an angle. And I will make you a more quantitative calculation for that. So let's look at this slit from above. Here's the slit. And the slit has an opening delta x. And this delta x we're going to make smaller and smaller. And let us start with a delta x of about 1/10 of a millimeter, which is 10 to the minus 4 meters. I have light, I know the wavelengths of the light, and I know the lambda equals h divided by p, according to de Broglie. I know the wavelengths, I know h, and so I can calculate the momentum of that light. I have done that, take my word for it, it is about 10 to the minus 27 kilogram meters per second. That's the momentum of the individual light photons. Think of them as particles, which you can do according to de Broglie. So now, I have a delta P. The degree to which the momentum is undetermined, according to Heisenberg, is going to be 10 to the minus 34 divided by delta x, which is 10 to the minus 4th. So that is 10 to the minus 30. Very small. But the momentum itself is 10 to the minus 27. So it's only 1 part in 1,000. So what will happen if the light comes through here, and I now make a classical argument. I say this is the momentum of the light as it comes straight in. When it has to be squeezed through this narrow opening, Heisenberg's uncertainty principle demands that it's going to be undetermined the momentum in this direction by roughly 10 to the minus 30 or more. Remember, it's always larger or equal. In other words, if I introduce, for instance, in this direction or in this direction, delta P, then I would expect that some of that light goes off in this direction. It is this change in momentum, this undeterminedness in momentum, that makes it go off in an angle. Only in the x direction. If I have this slit like this, don't expect this to happen in this direction, because the uncertainty in the y direction, that's not the problem. Delta y is not very small, it's delta x that is very small. So it's this direction that's going to give you trouble. It's only in this direction that you know precisely where that light goes through. This direction is not the issue. So this angle theta can now be calculated very roughly. Theta is obviously delta p divided by p. So theta is very roughly 10 to the minus 3 radians, which is a 15th of a degree. And if you have at a distance L, this distance here is L, if you have here a screen, then the spot on this screen, if I call that x at location L, then x at location L is obviously theta times L. And if theta is 10 to the minus 3, and let's assume this is about 10 meters away from us, so L is about 10 meters, then you get 10 to the minus 2 meters. That is 1 centimeter. 1 centimeter in this direction and 1 centimeter in that direction. 2 centimeters. But when I make the slit width 10 times smaller, if I make the slit width only 1/100th of a millimeter, then this becomes 10 centimeters. Because now I know delta x 10 times better, and so delta p is 10 times more uncertain. So now I expect to see here at least a smear of 20 centimeters and at least a smear of 20 centimeters there. So the absurdity is that a teeny weeny little light source, which in the beginning you will see as a very small spot, when I make this slit narrower and narrower, indeed you will see that you will lose photons, and you will see this getting narrower and narrower, and then all of a sudden it begins to spread out, and it begins to spread out, and by the time I'm close to a tenth of a millimeter, the light spot there will be yay big. Very non-intuitive. You make the slit smaller and the photons spread out. And I want to show that to you now. I have to make it very dark. And I need my flashlight. Turn on the laser beam. There you see it. The slit is now all the way open. Yeah, it's all the way open. And I'm going to close the slit now slowly. And if you look closely, you will see that the... Let me also get my red laser, then I can point something out. You will see that the light will get squeezed in the horizontal direction. You can see already that the left side has a very sharp vertical cutoff and the right side also. It's getting narrower, getting narrower, getting narrower, but I'm nowhere nearly a tenth of a millimeter yet. It's getting clearly narrower. You see it's getting narrower, it's it's getting narrower. Now, if I look here, oh, I'm not yet at the 10th of a millimeter, but I'm getting there. Going slowly, squeezing it. I'm squeezing those photons. Those photons now are forced to go through an extremely narrow opening. And Heisenberg is very shortly going to jump in and says, you're going to pay a price for that. You know too well where those photons are in the x direction, the price you pay, that nature will now make the momentum undetermined in the x direction. And you begin to see it now. You already begin to see that the center portion is widening. Even photons appear here. You see some dark lines, which I will not further discuss today, but notice that the light is spreading. Of course, when I squeeze this slit, when I make it narrower, it's obvious that I lose light, because the light that hits the side of the slits is not going through. So the light intensity will go down. That's just inevitable. I use fewer photons. But look at this. There are photons here, there are photons there. It's at least 10 centimeters, this portion. From here to here is at least 1 foot. I squeeze more. This is more than half a meter now. I squeeze more. This is about 1 meter already. Now, not only have you seen quantum mechanics at work in terms of electrons jumping between allowed energy levels, but you now have also seen one other very interesting consequence of quantum mechanics, which is Heisenberg's uncertainty principle. Now, the spreading of this light can very easily be explained without Heisenberg's uncertainty principle. In fact, it was known, even in the previous century, to a high degree of accuracy, why this happened, and the dark lines were very accurately explained. All I wanted to show is that this spreading of the light is entirely consistent with Heisenberg's uncertainty principle. And it better be, because it would not be possible, it would be inconceivable that you could do any experiment that would violate Heisenberg's uncertainty principle. And if this light that you would see on the screen there, if that light spot would get narrower and narrower and narrower and narrower all the time, as we would think classically, that would have been a violation of Heisenberg's uncertainty principle. And that is not possible. Now, there is no way in advance to predict which photons end up where. All you can do with quantum mechanics is to do the experiment with lots of photons, and then you will get a certain distribution, and the distribution will be exactly as you saw there. Quantum mechanics can never predict on an individual photon where it will end up. We saw that bright spot in the center. So if you did this experiment with 1 photon per day, 1 photon per day going through this slit, and you would have a photographic plate there, and you would keep it there for months, and you would develop it, you would see the same pattern that you see there. This photon arrives today. Here arrives 1 tomorrow. Here arrives 1 the day after tomorrow. Here 1 the day after that. 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 And slowly are you beginning to see that pattern that you saw. So don't think that this interference pattern that you saw is the result of 2 photons going through the slit simultaneously. Not at all. You can do it with 1 photon at the time, and you would see exactly the same thing. Now, this idea that you cannot in advance predict what a particular photon will do is a very non-classic idea. And it rubs us all the wrong way. Because our classical way of thinking is, and you are no different from my own feeling in this respect, that if you do an experiment 100 times in a controlled way, you should get 100 times exactly the same result. Not so, says quantum mechanics. All that quantum mechanics will tell you is what the probability is that something will happen. No guarantee, but it is very good in predicting probabilities. Now, Einstein had great problems with this idea of not knowing precisely what would happen, and he had endless discussions with Bohr and others in which he tried to convince them that because you couldn't predict what happened, that something had to be wrong with quantum mechanics. And Einstein's famous words were, "God does not throw dice." This was his way of saying it is ridiculous that the outcome of a well-controlled experiment is uncertain. Now, almost 9 decades have gone by since the beginning of quantum mechanics, and we now know that God, if there is one, does throw dice. However, God is bound to the rules of quantum mechanics and cannot violate Heisenberg's uncertainty principle. The light could not go straight through without spreading when I made the slit as narrow as I did. So quantum mechanics is a bizarre world that we rarely experience in our daily lives because we are used to basketball, baseballs, tennis balls. But yet, it is the way the world ticks. And atoms and molecules can only exist because of quantum mechanics. That means you and I can only exist because of quantum mechanics. I hope that this will give you something to think about. But I warn you in advance, because if you start thinking about this, it will give you headaches and it will give you sleepless nights. And it has given me countless sleepless nights in the past, and even today when I think about the consequences, the bizarre consequences of quantum mechanics, I still cannot comprehend it, I still cannot digest it, and I still have headaches and sleepless nights. But it may be necessary to go through these sleepless nights if you want to eventually evolve as an independent thinking scientist, and I hope that someday all of you will. Thank you.
The polarization of light plays a critical role in much of our technology, and it plays a very important role in experiments in quantum mechanics which challenge our assumptions about the nature of reality. In classical physics, light can be thought of as a wave of electric and magnetic fields. Suppose that we have 2 of these electromagnetic waves in the exact same region of space. At each point in space and time, their electric fields will add like vectors, and their magnetic fields will add like vectors. In this case, the 2 waves add together to form a new electromagnetic wave with a higher amplitude. Now let us consider a new scenario. We again have 2 electromagnetic waves in the same region of space, but this time they are not oriented in the same direction. As before, the electric field will add like vectors. And the magnetic fields will add like vectors. This time, the 2 waves add together to form a new electromagnetic wave with its orientation changed as shown. Now let us consider yet another scenario. This scenario is the same as the previous one. Except that in this case, one of the 2 original electromagnetic waves is ahead of the other one. As before, the electric fields will add like vectors. And the magnetic fields will add like vectors. This time, the new electromagnetic wave continuously rotates through space and time as shown. Now let's consider a slightly different scenario. This time, it is the other one of the two original electromagnetic waves which is ahead. In this case, they will add together to form a new electromagnetic wave that continuously rotates in the opposite direction of the previous scenario. If light consists of waves that are all continuously rotating in the same direction, we refer to it as circularly polarized light. On the other hand, if the light consists of electromagnetic waves that are all aligned in the same direction as shown, we refer to it as linearly polarized light. Most light sources, such as light bulbs, candles, and the sun, produce light that is composed of electromagnetic waves that are all oriented in different directions. We refer to this as unpolarized light. Each electromagnetic wave is composed of both an electric field and a magnetic field that are 90 degrees to one another. In order to help visualize the upcoming explanations, let us just show the electric field, though the magnetic field is still always present. Every electromagnetic wave can be thought of as the combination of two other electromagnetic waves, which are oriented in one of these two directions. There are some materials that block electromagnetic waves oriented in one of these directions, but allow electromagnetic waves that are oriented in the other direction to pass through. Therefore, regardless if it is circularly polarized, linearly polarized, or unpolarized light that enters the material, only linearly polarized light is able to exit the material. If the incoming light is already linearly polarized, and it is oriented in the direction in which the material blocks electromagnetic waves, then all the light will be blocked completely. On the other hand, if we rotate the material, then the direction in which the electromagnetic waves are blocked will also rotate, and the light will now pass through. Suppose we start out with unpolarized light. After it passes through the material, we will have linearly polarized light. We therefore refer to this material as a linear polarizer. Suppose we add another linear polarizer, as shown. Now suppose we rotate the second linear polarizer. If the two polarizers are 90 degrees to each other, no light is able to pass through. Now let us add a third linear polarizer, located in between the first two, as is shown. Suppose we rotate this third linear polarizer by some amount between 0 and 90 degrees. Its axis for blocking light and for allowing light to pass through will rotate as shown. The linearly polarized light entering this polarizer can be thought of as a combination of two electromagnetic waves, each aligned along one of the polarizer's two axes. Only one of these two electromagnetic waves will pass through. Therefore, the net result is that the total electromagnetic wave has been rotated from its previous orientation. The new electromagnetic wave leaving this polarizer can also be thought of as the combination of two other electromagnetic waves, oriented as is shown. One of these two waves has the ability to pass through the next linear polarizer. When we started out with just two linear polarizers rotated 90 degrees to each other, no light was able to pass through. But when a third linear polarizer was added in between them, now light is able to pass through our three polarizers. The amount of light that is able to pass through depends on the angle of this third linear polarizer in between the first two. In empty space, light always travels at the same speed from the perspective of all observers. But light can slow down when it passes through a material. In the case of some materials, light will slow down by a different amount depending on which direction the electromagnetic wave is oriented. Suppose that the difference by which the waves are slowed down is 1/4 of a wavelength. In this case, we refer to the material as a quarter wave plate. When linearly polarized light passes through a quarter wave plate at a 45-degree angle to the wave plate's two axes, the wave can be thought of as being composed of two different electromagnetic waves, one of which is slowed down by a quarter wavelength more than the other. The waves leaving the quarter wave plate add together as vectors. When linearly polarized light passes through a quarter wave plate, it is converted into circularly polarized light. If the circularly polarized light passes through another quarter wave plate, the incoming circularly polarized light can also be thought of as two waves, one of which is slowed down by a quarter wavelength more than the other. Therefore, when circularly polarized light passes through a quarter wave plate, it is converted back into linearly polarized light. Quarter wave plates convert linearly polarized light into circularly polarized light, and they convert circularly polarized light back into linearly polarized light. The phenomena described here plays a very important role in much of our technology. And it plays a very important role in experiments in quantum mechanics which challenge our assumptions about the nature of reality. Much more information is available in the other videos on this channel, and more videos will be coming soon.
Light is an electromagnetic wave where the electric and magnetic fields are oscillating perpendicular to the direction of movement of light. Light from a source vibrates in many planes. Light vibrating in many planes is called unpolarized light. However, it is possible to make light vibrate in only one plane. Now, if we look at the light directly from the source, the vibrations seem to go up and down like this. So this two-headed arrow can represent the vibrating plane. Light wave in a single plane is called polarized light. Now we will pass this unpolarized light through an instrument called the polarimeter. The polarimeter has got two Polaroid filters. The first one is called a polarizer and the second one is called an analyzer. When light passes through the polarizer, the light that is passed through vibrates in only one plane. The other vibrations are either completely or partially cut off. The emerging light vibrates in only one plane and hence it is polarized light. Polarized filters have molecules arranged in a specific order that allows a light to pass through in only one plane. If the alignment of the polarizer is same as that of the analyzer, then we will see light glow through the eyepiece. Now the Polaroid filter of the analyzer is rotated through an angle of 90 degrees such that the analyzer's molecules are now perpendicular to the plane of the polarized light, resulting in no vibrations passing the analyzer, and we see darkness in the eyepiece. Now, if the polarized light is passed through an optically active compound kept in the sample tube, then the plane of the polarized light rotates and hence the darkness in the eyepiece is not there anymore. Darkness only exists when the analyzer is exactly perpendicular to the plane polarized light. We rotate the analyzer till we see darkness again in the eyepiece. This occurs when the analyzer is perpendicular to the plane of the rotated light. Let's assume that the initial direction of the plane polarized light coming from the polarizer is this. In the beginning, the analyzer is kept parallel to the polarizer, and hence all the light will pass through the analyzer too. If we rotate the analyzer by an angle other than 90 degrees, sunlight will still pass through, but its intensity will be reduced. But if we rotate the analyzer by an angle of 90 degrees to the initial direction, then the entire light will be cut off. One of the most accurate and commonly used polarimeter is the Lorentz half-shade polarimeter. It consists of a monochromatic source S, which is placed at a focal point of a convex lens L. Just after the convex lens, there is a Nicol prism P, which acts as a polarizer. H is a half-shade device which divides the field of polarized light emerging out of the Nicol P into two halves of perpendicular plane. T is a glass tube in which optically active solution is filled. The light after passing through T is allowed to fall on the analyzer Nicol A, which can be rotated about the axis of the tube. The rotation of the analyzer can be measured with the help of a circular scale C, and this E is the eyepiece. To understand the need of a half-shade device, let us suppose that half-shade device is not present. The position of the analyzer is so adjusted that the field of view is dark when the tube is filled with only with deionized water. The position of the analyzer is noted on a circular scale. Now the tube is filled with optically active solution and it is set in its proper position. The optically active solution rotates the plane polarization of the light emerging out of the polarizer P by some angle. So the light is transmitted by the analyzer A and the field of view of telescope becomes again bright. Now the analyzer is rotated by a finite angle so that the field of view of telescope again becomes dark. This will happen only when the analyzer is rotated by the same angle by which plane of polarization of light is rotated by optically active solution. The position of the analyzer is again noted. The difference of the two readings will give you the angle of rotation of plane polarization. A difficulty is faced in the above procedure that when the analyzer is rotated for the total darkness, then it is attained gradually and hence it is difficult to find the exact position correctly by which complete darkness is obtained. For example, if the total darkness is attained at 20 degree clockwise, then at 19.9 and 20.1, it will be difficult to tell which is more darker than the other since there is nothing to compare it with. The half-shade device consists of two semicircular halves of equal size. One half is made up of plain glass and the other is made up of quartz. Without going into too much detail as we are talking about this experiment from the point of view of chemistry, it will suffice to say that the plane polarized light coming out of the glass will remain in the same plane while that coming from the quartz will get rotated by 90 degrees. When no optically active substance is present, if the principal axis of the analyzer is parallel to that of the polarizer, the glass half becomes bright while the quartz half becomes dark. If the analyzer is rotated by 90 degrees, then the quartz half becomes bright and the glass half will be dark. The analyzer is kept exactly midway between these points where both halves will be equally bright, and this brightness will be lower than the maximum brightness of each half individually. It is easier to compare two bright semicircles rather than try to achieve complete darkness of bright circle absolutely. This is the Lorentz half-shade polarimeter. Prepare the solution of the substance whose optical activity is needed to be determined. Next, clean the polarimeter sample holder with deionized water. Next, we must calibrate the polarimeter with deionized water. To do this, we must fill the sample holder up to the top with deionized water and ensure that there are no bubbles. Next, open the hatch to place the sample holder. Close the hatch and observe through the eyepiece. To ensure calibration, make sure the two semicircular halves are of equal brightness. Make sure that the inner and outer scales have their zeros aligned. If not, align them by moving the inner scale. This implies that the machine is calibrated. Next, after discarding the deionized water, fill the sample holder with the solution of the sample. Place the sample holder in the polarimeter. As done before, adjust the dial to see the two semicircular halves with equal brightness. Now note the value of rotating using first the outer dial. The outer scale is the whole number for the observed rotation reading, and the inner scale is for the first two places of decimal reading. Look for the outer scale reading which meets up with the zero of the lower scale reading. If it exactly meets a line, then note the value of the outer scale. If it is in between two values, then use the lower value. In this example, the whole number is 1. To know the decimal point, look at the mark on the inner scale that exactly matches a mark of the outer scale. In this example, the decimal number is 1. So in this case, the reading is 1.1. If you take the reading on the left side of the machine and the inner scale 0 is above the outer scale 0, then the rotation is negative. And if you take the reading on the right side, then it will be the other way around. Meaning if the 0 of the inner scale is below the 0 of the outer scale, it is negative reading. Why are chiral molecules optically active and achiral molecules not? We need to understand certain points. First, a molecule that has a net dipole moment will rotate the plane polarized light, and it will do so always. Just because molecules of a compound rotate the plane polarized light does not make the compound optically active. A molecule not having a net dipole moment will not rotate the plane polarized light. A molecule that has net dipole moment has an electric field. This electric field vector interacts with the electric field vector of the plane polarized light and by some mechanism rotates its plane. The mirror image of a molecule having net dipole moment will always rotate the plane polarized light in the direction opposite to that of the molecule. Now let's take an example of an achiral molecule. It is achiral because it has a plane of symmetry. Let us assume that a plane polarized light approaches this molecule from the front side And let us say it interacts with the molecule from the front. And let us also assume that as it passes through this molecule, it will get rotated because the molecule has a net dipole moment. Let's also assume that this light is rotated to the left, like this. If you were to reverse this animation, it would tell us what would this light behave if it were to approach this molecule from the back. If this light were to approach this molecule from the back side, in between these two white atoms, it will move towards the green. Therefore, when it passes through this molecule, it moves like this. And let us assume that in front of this molecule, after light has been turned to the first one, you find the mirror image of the molecule. So now it is going to approach the second molecule in this direction. And since it has already been turned by the first molecule, it will now move towards the green as it did so in the first one. And therefore the molecule rotates it such a way that it moves towards the green and the plane becomes the same as the one before hitting the first molecules. So in this case, in the achiral molecule, the mirror image of the molecule is going to cancel the rotation of the first molecule. And statistically speaking, that out of several billions and billions of molecules, that there is always a mirror image existing for each and every molecule. So in effect, the net optical effect is zero. So even though each molecule did rotate the plane polarized light, either clockwise or anti-clockwise, the net rotation is zero and the molecule is said to be optically inactive. Now let us take the example of a chiral molecule. As you can see, this molecule does not have any plane of symmetry. Let's assume that a plane polarized light hits the molecule from the front side. Once it passes through, let us also assume it tilts towards the olive atom. Which means when it approaches the molecule from the back side, that is in between white and olive, it will tilt towards the white and therefore go back to vertical. So now it turns left after meeting molecule 1. Now in a sample of a pure chiral molecule, the molecules will not be mirror images of each other. Therefore, it will encounter a same molecule which is not a mirror image of the first one. Now this molecule is just this molecule which has been rotated. Remember, the light when it passes through this white and olive, it will tilt towards the white. So when this light approaches the second molecule, it is going to move towards white, which implies that the optical rotation is enhanced. So whatever is the rotation of the first molecule, the second molecule doubles it. So there is no cancellation of optical rotation. And this also proves that the optical rotation is directly proportional to the number of molecules it interacts with.
DNA is a molecule made up of two strands, twisted around each other in a double helix shape. Each strand is made up of a sequence of 4 chemical bases, represented by the letters A, C, G, and T. The 2 strands are complementary. This means that wherever there's a T in one strand, there will be an A in the opposite strand, and wherever there's a C, there will be a G in the other strand. Each strand has a 5' end and a 3' end. The 2 strands run in opposite directions. This determines how each strand of DNA is replicated. The first step in DNA replication is to separate the 2 strands. This unzipping is done by an enzyme called helicase and results in the formation of a replication fork. The separated strands each provide a template for creating a new strand of DNA. An enzyme called primase starts the process. This enzyme makes a small piece of RNA called a primer. This marks the starting point for the construction of the new strand of DNA. An enzyme called DNA polymerase binds to the primer and will make the new strand of DNA. DNA polymerase can only add DNA bases in one direction, from the 5' end to the 3' end. One of the new strands of DNA, the leading strand, is made continuously, the DNA polymerase adding bases one by one in the 5' to 3' direction. The other strand, the lagging strand, cannot be made in this continuous way because it runs in the opposite direction. The DNA polymerase can therefore only make this strand in a series of small chunks called Okazaki fragments. Each fragment is started with an RNA primer. DNA polymerase then adds a short row of DNA bases in the 5' to 3' direction. The next primer is then added further down the lagging strand. Another Okazaki fragment is then made, and the process is repeated again. Once the new DNA has been made, the enzyme exonuclease removes all the RNA primers from both strands of DNA. Another DNA polymerase enzyme then fills in the gaps that are left behind with DNA. Finally, the enzyme DNA ligase seals up the fragments of DNA in both strands to form a continuous double strand. DNA replication is described as semi-conservative because each DNA molecule is made up of one old, conserved strand of DNA and one new one. Here is a cell, the basic unit of all living tissue. In most human cells, there is a structure called the nucleus. The nucleus contains the genome. In humans, the genome is split between 23 pairs of chromosomes. Each chromosome contains a long strand of DNA, tightly packaged around proteins called histones. Within the DNA are sections called genes. These genes contain the instructions for making proteins. When a gene is switched on, an enzyme called RNA polymerase attaches to the start of the gene. It moves along the DNA, making a strand of messenger RNA out of free bases in the nucleus. The DNA code determines the order in which the free bases are added to the messenger RNA. This process is called transcription. Before the messenger RNA can be used as a template for the production of proteins, it needs to be processed. This involves removing and adding sections of RNA. The messenger RNA then moves out of the nucleus into the cytoplasm. Protein factories in the cytoplasm, called ribosomes, bind to the messenger RNA. The ribosome reads the code in the messenger RNA to produce a chain made up of amino acids. There are 20 different types of amino acid. Transfer RNA molecules carry the amino acids to the ribosome. The messenger RNA is read 3 bases at a time. As each triplet is read, a transfer RNA delivers the corresponding amino acid. This is added to a growing chain of amino acids. Once the last amino acid has been added, the chain folds into a complex 3D shape to form the protein.